The role of pressure in star formation. In the vast darkness between galaxies, where silence hangs heavier than time itself, lies the cradle of creation, the molecular cloud. These sprawling regions of cold hydrogen gas and interstellar dust, often stretching for hundreds of light years, are the birthplaces of stars. Though they appear calm from afar, inside them an invisible battle rages. At the heart of this cosmic conflict is pressure, a force that, while intangible, has sculpted the architecture of the universe. Pressure in star formation begins as a quiet whisper, almost imperceptible. Within a molecular cloud, random fluctuations and turbulence, triggered by galactic interactions or the shock waves from distant supernovae, cause certain regions to become denser than their surroundings. These dense pockets, known as prestellar cores, are fragile at first, delicately balanced between the inward pull of gravity and the outward push of thermal pressure, but gravity, relentless and patient, begins to tip the scale. As matter accumulates and compresses, gravitational pressure builds. It crushes the gas inward, reducing the volume and increasing the density. This rise in pressure leads to an increase in temperature. The molecules, once drifting freely, begin to collide with growing frequency and intensity at a critical threshold. Deep within the core, the pressure reaches a point where it overcomes all forms of resistance. This is known as the Jeans instability, a pivotal moment in astrophysics, named after British physicist James Jeans. It describes the tipping point where the internal pressure can no longer counteract gravity, and collapse becomes inevitable. During this collapse, gravitational potential energy is converted into thermal energy. The pressure and temperature skyrocket, particularly in the central region of the core. As the collapse accelerates, conservation of angular momentum causes the infalling gas to form a rotating disk around the growing protostar. This disk, rich in gas and dust, becomes a feeding ground for the infant star at the center. But it is still not yet a star. For a protostar to ignite into a true star, the pressure must rise to extraordinary levels. In the core, hydrogen atoms are forced so close together that quantum mechanics begins to dominate. Under such immense pressure, millions of times greater than the pressure at Earth's surface, hydrogen nuclei begin to fuse into helium. This fusion releases enormous amounts of energy, which radiates outward, generating radiation pressure. When this radiation pressure balances the inward gravitational force, hydrostatic equilibrium is achieved. It is in this moment that the star is born. The role of pressure does not end at ignition. It continues to govern the star's life, defining its size, brightness, and longevity. Massive stars have much higher core pressures and temperatures, causing them to burn through their nuclear fuel in mere millions of years. Smaller stars with lower internal pressure can burn for tens of billions of years. In all cases, pressure is the regulator, the constant force sculpting a star's structure and determining its fate. Beyond individual stars, pressure shapes stellar nurseries into clusters and associations. Feedback from new stars, stellar winds, ultraviolet radiation, and eventually supernovae, injects energy into the surrounding gas, increasing local pressure and triggering the next generation of star formation. This cyclical dance of compression and collapse weaves the luminous tapestry of our galaxy. Even dark matter, the enigmatic scaffolding of the universe, plays an indirect role in this pressure-driven process. By providing additional gravitational wells, dark matter influences the density structure of galaxies, enabling more efficient collapse of gas clouds into stars. Though it does not interact with normal matter via pressure in the conventional sense, its gravitational fingerprint deepens the potential wells in which pressure-driven star formation unfold. Ultimately, pressure is not merely a physical parameter in astrophysical equations. It is a storyteller. It records the hidden history of molecular clouds, reveals the secrets of nuclear fusion, and determines the life story of every star we see in the sky. Without pressure, there would be no starlight, no warmth, no planets, no life. It is the invisible breath that stirs the cosmic forge into flame. Temperature thresholds for nuclear fusion. As gravitational pressure sculpts the structure of a newborn star, compressing matter with relentless intensity, another silent force begins to awaken. Temperature in the depths of the collapsing core, where atoms are pressed into a shrinking volume, collisions grow more violent. Molecules can no longer remain intact, and atoms are stripped of their electrons, forming a dense plasma of bare nuclei and free-roaming electrons. This seething state is no longer just matter. It is a crucible, and within this crucible, temperature becomes the gatekeeper of transformation. Temperature, in the astrophysical sense, is not simply a measure of heat. It is the measure of kinetic energy, the chaotic motion of particles. In the high-pressure environment of a collapsing protostar, the kinetic energy of hydrogen nuclei must climb to extreme levels before fusion can even be considered. The reason lies in the nature of the atomic nucleus. Each nucleus carries a positive charge, and as like charge is repelled, two hydrogen nuclei naturally resist coming close. This is known as the Coulomb barrier, and overcoming it requires an immense amount of energy that only incredibly high temperatures can provide. As the core's density climbs under gravity's hand, the temperature rises into the realm of millions of degrees. At around 10 million Kelvin, a threshold found through decades of theoretical modeling and observational inference, hydrogen nuclei, particularly isotopes like protium and deuterium, begin to slam together with enough speed to overcome their mutual repulsion. When they do, the strong nuclear force, which binds protons and neutrons inside atomic nuclei, takes over and fuses the nuclei together. In that instant, some mass is lost, converted directly into energy, as dictated by Einstein's equation, E=mc². This process is the beginning of nuclear fusion, the reaction that powers every star in the night sky. But not all fusion is the same. The temperature threshold determines which kind of fusion reaction dominates. In smaller stars like our Sun, the primary fusion pathway is the proton-proton chain. This reaction occurs at relatively lower temperatures, between 10 and 15 million Kelvin. But even this is scorching beyond human comprehension. Larger, more massive stars can reach internal temperatures exceeding 20 million Kelvin or more, enabling a faster and more efficient reaction known as the CNO cycle, where carbon, nitrogen, and oxygen atoms act as catalysts in the fusion of hydrogen into helium. Beyond hydrogen, the fusion of heavier elements requires even higher temperatures. Helium fusion, or the triple ALMA process, begins at approximately 100 million Kelvin, producing carbon and oxygen. In the later stages of a massive star's life, when the hydrogen and helium have been largely consumed, temperatures in the core can rise to several 100 million Kelvin. At these blistering levels, elements like carbon, neon, and silicon undergo fusion, producing ever heavier nuclei, leading up to iron, the endpoint of exothermic fusion. Iron, however, is a threshold. Fusing it does not release energy, it consumes it. This sets the stage for collapse. But before that, it marks the limit of what temperature and fusion can achieve inside a living star. The role of temperature in this process is not just to ignite fusion, it is to determine the star's entire evolutionary path. The rate of nuclear burning, the balance of elements, the intensity of radiation pressure, and the stability of the core. All are ruled by temperature. Understanding these thresholds has not come easily. It has required decades of observational astrophysics, particle accelerator experiments, and solar neutrino detection. In the mid-20th century, astrophysicists like Hans Bethe laid the theoretical groundwork for nuclear fusion in stars, predicting the energy yields and temperature requirements. These ideas were confirmed through solar models and later by the direct detection of neutrinos, ghostly particles emitted during fusion, giving us a glimpse into the sun's burning heart. The practical implications of these temperature thresholds stretch far beyond theory. On Earth, scientists have long attempted to replicate stellar fusion in controlled environments, striving to reach the same temperature benchmarks required in stars. Facilities like the Joint European Torus and ITER are attempting to sustain plasma at over 100 million Kelvin, hoping to achieve net energy gain through fusion. Yet the same challenges that stars overcome with gravity, achieving confinement and pressure, require advanced magnetic or inertial systems on Earth. The stars fuse effortlessly. Humanity must build machines the size of cities to come close. In this cosmic narrative, temperature is not just a number. It is the switch that turns gravity's sculpting into fire, the threshold between collapse and brilliance. It is the force that defines not just the life of a star, but the elements it creates, the light it emits, and the story it leaves behind in its remnants. Once fusion begins, the core of a star becomes a raging furnace, balancing pressure and gravity in a delicate equilibrium. But eventually, this balance will fail, and the star's life will reach its final act, a violent end, triggered by a sudden collapse of pressure and a catastrophic surge in temperature. And it is in that climactic moment, when fusion halts and gravity takes over unchecked, that we enter the realm of supernovae, the next chapter in this elemental saga. Supernovae, pressure collapse, and thermal explosion. The life of a star is a prolonged war between two forces: gravity pulling inward and pressure pushing outward. For most of a star's life, nuclear fusion within its core supplies the energy to maintain equilibrium. As hydrogen fuses into helium, the energy released produces outward pressure that counters the star's own gravity, allowing it to shine steadily for millions or even billions of years. But this balance is temporary. Eventually, the nuclear fuel begins to run out. When it does, the internal pressure that once resisted collapse fades and gravity reclaims its ancient dominion. What follows is one of the most violent events in the universe: a supernova. The journey toward a supernova begins in the hearts of massive stars, many times heavier than the Sun. These stellar giants burn through their nuclear fuel at a furious pace. After exhausting their hydrogen, they begin fusing helium into carbon, then carbon into oxygen, and so on, building an onion-like structure of concentric layers, each fusing heavier elements. At each stage, higher temperatures and pressures are required to sustain fusion. This progression culminates in the fusion of silicon into iron in the core. Current, however, marks a dead end. Unlike lighter elements, the fusion of iron does not release energy, it absorbs it. Once a star's core is predominantly iron, no further fusion reactions can generate the pressure needed to hold up the immense weight of the overlying layers. Gravity, no longer opposed by thermal pressure, takes over in a matter of seconds. The core collapses inward at nearly a quarter the speed of light. Densities soar, and atoms are crushed so tightly that protons and electrons merge into neutrons, releasing a flood of neutrinos in the process. This implosion halts only when the core becomes so densely packed with neutrons that further compression is resisted by quantum forces, specifically neutron degeneracy pressure. But by then, the outer layers of the star, still hurtling inward due to the collapse, slam into the incompressible neutron-rich core. This violent collision triggers a shockwave, sending an explosive burst of energy outward. The result is a supernova, a cataclysmic explosion that releases more energy in a few seconds than the Sun will emit in its entire lifetime. The outer layers of the star are blasted into space at speeds of thousands of miles per second, enriching the cosmos with heavy elements forged during the explosion. Gold, platinum, uranium, all these rare elements owe their existence to the high-energy crucible of a supernova. What was once a quiet, fusion-powered star becomes a radiant, expanding nebula, visible across entire galaxies. Supernovae come in different types, depending on their origin. The collapse of a massive star leads to what is called a Type II supernova, characterized by the presence of hydrogen in its spectrum. In contrast, some stars in binary systems undergo a different kind of explosion. Type A supernovae. In these scenarios, a white dwarf accretes matter from a companion star until it reaches a critical mass, triggering a runaway thermonuclear explosion that obliterates the star entirely. Despite their variety, all supernovae share a common essence: the catastrophic failure of pressure to contain gravity's inward pull. They are sudden deaths, but also cosmic births, giving rise to neutron stars, black holes, and the elemental diversity necessary for planets and life. Without supernovae, there would be no iron in human blood, no calcium in bones, no silicon in Earth's crust. They are not merely destructive, they are the engines of cosmic renewal. Supernovae also leave behind profound remnants. Expanding clouds of ionized gas and dust, such as the Crab Nebula, serve as glowing tombstones of once mighty stars. Their shockwaves propagate through interstellar space, compressing nearby molecular clouds and often triggering new waves of star formation. Thus, from destruction emerges creation, an endless cycle driven by the physics of collapse and explosion. Modern astronomy has learned to observe and study these events with increasing precision. High-energy observatories like Chandra and NuSTAR have captured the X-ray glow of supernova remnants, while radio telescopes map their magnetic fields. In recent years, astronomers have even detected the gravitational waves from the collapse of neutron stars, ripples in the fabric of space-time caused by these cosmic convulsions. The supernova stands as the ultimate testament to the power of pressure and temperature. It is what happens when fusion falters, when equilibrium is lost, and when the universe decides to reset the balance through an outburst of unimaginable energy. It is both a tomb and a womb, a place where one star ends and countless new possibilities begin. Yet not all explosive pressure systems are fueled by such dramatic endings. Some worlds, like the gas giants in our solar system, sustain massive internal pressures not through collapse, but through sheer mass and composition. Deep within their atmospheres, layers of pressure build silently, shaping strange, exotic interiors. And it is there, within the crushing depths of planets like Jupiter, that the story continues as we explore how pressure acts not in death, but in planetary life itself. Gas giants and their internal pressure systems. In the wake of stellar cataclysms like supernovae, matter scattered across interstellar space does not drift aimlessly. It gathers, coalesces, and reorganizes itself under the same ancient laws that govern stars. And within this cosmic ballet, not all gravitational conquests lead to fiery cores or nuclear ignition. Some massive objects form a different kind of monument to pressure, silent, cold, and shrouded in cloud. These are the gas giants, and within their depths lies a kingdom of pressure so immense it can transform the very nature of matter. Gas giants like Jupiter and Saturn are not failed stars, though their massiveness and composition hint at shared origins. These planetary titans formed from the protoplanetary disks left behind by young stars, where abundant hydrogen and helium condensed into enormous envelopes surrounding smaller, rocky or icy cores. Unlike terrestrial planets, gas giants never ignited nuclear fusion in their centers, yet their sheer mass created a gravitational grip strong enough to crush their interiors into exotic states unknown on Earth. In the upper layers of these planets, the atmosphere is dominated by molecular hydrogen and helium, floating above clouds of ammonia, water, and methane. But as one descends deeper beneath the visible cloud tops, the pressure increases relentlessly. The weight of the gas above exerts a constant and growing force, compressing the material below into ever denser phases. This is no ordinary weather system. It is a vertical column of atmospheric compression that extends tens of thousands of miles downward. Inside Jupiter, for example, pressures grow so extreme that hydrogen, the lightest and most common element in the universe, undergoes a profound transformation. Under pressures reaching several million times that of Earth's surface, molecular hydrogen is squeezed so tightly that electrons are freed from their nuclei, turning the fluid into metallic hydrogen, a rare electrically conductive state predicted by quantum physics and only recently recreated in laboratory conditions. This exotic metallic form is thought to behave like a liquid metal and is believed to be responsible for Jupiter's incredibly powerful magnetic field, the strongest of any planet in the solar system. This transformation is not merely a curiosity, it is a window into the fundamental behavior of matter under crushing force. Metallic hydrogen is a super-dense conductor that may exhibit superconductivity and superfluidity at certain pressures and temperatures. In Jupiter, it may extend across a vast inner shell that encircles the dense core, driving internal currents and influencing the planet's magnetic dynamo. Saturn, slightly less massive than Jupiter, likely also harbors metallic hydrogen in its depths, though the pressures and temperatures may differ subtly, resulting in variations in magnetic field structure and atmospheric dynamics. The interplay between mass, composition, and internal pressure defines not only the interiors but the very character of these planets. Their bands, storms, auroras, and radiation belts all trace their origins back to pressure-driven processes deep within. These internal systems are not static. As the gas giants slowly cool over billions of years, the internal heat, a relic of their formation and continued gravitational contraction, seeps outward. This thermal flux helps sustain convection within the fluid layers, allowing the internal pressure systems to remain dynamic. In Jupiter and Saturn, this contributes to the continuous churning of atmospheric bands and the persistence of long-lived storms like Jupiter's Great Red Spot. Uranus and Neptune, the ice giants, offer a variation on this theme. Though less massive and composed of a higher proportion of heavier elements like water, ammonia and methane, their interiors are still governed by staggering pressures. Deeper inside these planets, it is believed that water may exist in a superionic state, an exotic phase where hydrogen ions move freely through a rigid lattice of oxygen atoms. Such forms of matter arise only under intense compression and temperature, highlighting once again how pressure acts as a sculptor of the extraordinary. This brings us to the alternate, provocative, and alternate. Understanding these pressure systems is not only a matter of planetary science, it is a pursuit that touches on material physics, fluid dynamics, and magneto-hydrodynamics. Simulations and laboratory experiments on Earth attempt to recreate the high-pressure environments of gas giants to verify theories about their interior. These studies push the boundaries of human knowledge, challenging our understanding of states of matter and offering insights that extend into broader astrophysical questions. Gas giants are also time capsules, preserving the primordial materials of the early solar system. Their massive atmospheres retain signatures of the original nebula from which our system was born. The way pressure shapes their interiors and atmospheres reveals not only the mechanics of planetary formation, but also the diversity of worlds that may exist across the galaxy. Exoplanet surveys have revealed hundreds of Jupiter-like and even larger gas giants orbiting distant stars. Some heated to extremes, some flung into wild orbits, each one with internal pressures sculpted by its unique origin story. And in the most extreme among them, planets that orbit close to their stars, heated until their atmospheres expand and boil away, pressure plays a different role, fighting against radiation and gravity in a constant tug-of-war. These are the hot Jupiters, the next step in our exploration. In them, pressure not only shapes the internal dynamics but also influences entire atmospheric envelopes in ways unseen in our solar system. As we turn to these alien giants, we find that the power of pressure is not only buried deep within, but also expressed in the swirling, turbulent skies far above. You said high-pressure chemistry inside exoplanets. As we extend our gaze beyond the solar system, we enter a realm teeming with planetary diversity, a tapestry of worlds where the familiar laws of physics meet unfamiliar extremes. Among these distant orbs are exoplanets, planets orbiting stars beyond our Sun, many of which exist under conditions far more intense than anything within our own cosmic neighborhood. Within their vast and often massive interiors, pressure becomes not merely a physical parameter, but a transformative agent of chemistry itself. Here, in the dark, crushing depths of these alien worlds, molecules rearrange, elements fuse into unrecognizable compounds, and new phases of matter emerge, ushering us into the frontier of high-pressure chemistry. On Earth, chemistry unfolds under relatively gentle conditions. Molecular bonds form and break in predictable ways, governed by room temperature and atmospheric pressure. But as we move beneath the surface of a super-Earth, or into the cores of hot Jupiters, pressure can climb to levels unimaginable on our home planet, millions or even billions of times greater than what we experience on the surface. Under such crushing force, atoms are not merely pushed together, they are forced into entirely new configurations. Electrons are stripped from their shells, atomic radii shrink, and the very fabric of chemical identity is stretched to its limits. In these exotic environments, the traditional rules of valency and molecular stability are rewritten. For example, under extreme pressure, elements that are normally inert on Earth may become chemically active. Noble gases such as xenon, typically unreactive, can be forced into forming stable compounds with metals or oxygen. Sodium, an element familiar in table salt, transforms into a transparent insulator under pressure, defying its normal metallic behavior. Even water, the most essential and studied compound on Earth, adopts unfamiliar crystalline forms under pressure, forming phases like Ice 7 or Ice X, solids that exist not because of cold, but because of extraordinary compression. This pressure-induced transformation of matter plays a crucial role in defining the internal makeup and evolution of many exoplanets. Super-Earths, which possess masses several times that of Earth, are expected to have deep mantles and cores where high-pressure phases of silicates, carbonates, and iron alloys dominate. In these layers, common Earth minerals such as olivine or pyroxene morph into denser structures like perovskite or post-perovskite. These materials exhibit radically different physical properties, conducting heat, deforming, and even responding to magnetic fields in ways that influence the entire geological behavior of the planet. One of the most fascinating frontiers in high-pressure planetary chemistry is the behavior of carbon-rich worlds. In some exoplanets, especially those formed in regions of their protoplanetary disks with high carbon-to-oxygen ratios, carbon becomes the primary building block. Under massive pressure, carbon can organize itself not only into diamonds, the most stable form, but potentially into superdense polymers or even metallic carbon phases that may never exist naturally on Earth. Such diamond-rich planets may have internal structures layered with carbon allotropes, creating interior pressure profiles that differ wildly from silicate-based planets like our own. These high-pressure materials affect not only the composition but the dynamics of planetary interiors. The ability of a material to conduct heat, store energy, or resist deformation under pressure determines how heat escapes from a planet's core, how mantle convection operates, and whether a magnetic field is sustained over billions of years. In turn, these processes influence tectonic activity, volcanism, and the recycling of materials between surface and interior, all of which are critical to the potential for habitability. Our understanding of these chemical transformations does not rely solely on theory. Over the past few decades, high-pressure laboratories on Earth have been at the forefront of reproducing planetary conditions. Using diamond anvil cells, scientists can generate pressures approaching those found in exoplanetary cores, compressing samples between gem-grade diamonds to study how atoms behave in extreme environments. Coupled with high-powered lasers and synchrotron radiation, these experiments reveal phase transitions, bond rearrangements, and conductivity changes in real time, offering a glimpse into the alien chemistries shaping distant worlds. Astronomical observations add another layer to this puzzle. By studying the mass, radius, and density of exoplanets, scientists infer internal structures and compositions. Spectroscopic studies of atmospheres provide chemical fingerprints, while thermal emissions reveal heat flow that may hint at exotic interior processes. The James Webb Space Telescope and upcoming missions promise to deepen this understanding, allowing us to test high-pressure chemical predictions against the data gathered from real, far-off worlds. Yet despite all we've learned, the high-pressure interiors of exoplanets remain largely unexplored territory, a hidden domain where the familiar becomes foreign and every element behaves like a stranger. Here, pressure is not merely a modifier of chemistry, it is a creator of entirely new realities, a force that can push matter into states with no earthly counterpart. As we seek to understand these planetary hearts, another realm beckons just below the surface of our own world. There, hidden beneath the crust, lie vast regions where temperature and pressure interact in a different but no less complex dance. The gradients beneath Earth's surface hold secrets of their own, driving plate tectonics, feeding volcanic systems, and regulating the flow of heat that keeps our planet geologically alive. And so our exploration continues, from the deep hearts of alien worlds to the unseen engines beneath our feet. Thermal gradients beneath Earth's crust. While the high-pressure chemistries of distant exoplanets illuminate the extremes of planetary behavior, a subtler yet equally powerful narrative unfolds beneath our very feet. Here on Earth, the crust, the outermost shell of solid rock, is merely a thin veneer draped over a dynamic and restless interior. Beneath it lies a realm where temperature and pressure rise together in an intricate and layered ballet, giving rise to what geophysicists call thermal gradients. These invisible slopes of heat, increasing with depth, are not just geological curiosities. They are the engines that power tectonics, shape the continents, and sustain the magnetic field that protects life itself. The thermal gradient is, in essence, a measure of how temperature changes with depth beneath the surface. On average, for every mile one descends into Earth's interior, the temperature increases by roughly 20 to 25 degrees Celsius. However, this rate is far from uniform. It varies based on location, crustal thickness, rock type, and the presence of groundwater or magma. In tectonically active regions like mid-ocean ridges or volcanic arcs, the gradient is steep and volatile. In more stable continental interiors, it is shallower, but no less significant over geological time. This rise in temperature is not superficial. It stems from a variety of deep-seated sources. The first is residual heat from Earth's formation, an ancient warmth left over from the planet's violent birth in the early solar system. During Earth's accretion, planetesimals and protoplanets collided, releasing tremendous amounts of energy. That heat, though slowly dissipating, still lingers in the deep mantle. The second source is the decay of radioactive isotopes, primarily uranium, thorium, and potassium. As these elements break down, they release heat which seeps outward over millions of years. The third contributor is gravitational differentiation, the ongoing compression of Earth's interior due to its own weight, which continues to produce heat at depth. These combined sources create a stratified temperature profile stretching from the cool upper crust through the plastic mantle and into the molten outer core. This gradient is what makes plate tectonics possible. As heat rises from the mantle, it creates convection currents that slowly shift the rigid plates of the lithosphere. These movements drive continental drift, mountain formation, ocean trench subduction, and earthquakes, phenomena that define the geological history of our world. Yet the thermal gradient also governs more intimate and subtle features. In regions of high geothermal activity, such as Iceland or the Pacific Ring of Fire, the shallow gradient allows for hot springs, geysers, and volcanic eruptions. These are not just spectacles of nature. They are direct expressions of the internal heat gradient seeking equilibrium with the surface. In contrast, in continental shields like Canada or Siberia, where the crust is thick and ancient, the gradient is subdued and geothermal activity is minimal. One of the most profound implications of Earth's thermal gradients lies in its role in mantle convection. The mantle, though solid by conventional standards, behaves plastically over long timescales. As hot material rises and cooler material sinks, vast cells of convective motion circulate slowly beneath the lithosphere. These motions not only redistribute heat, but also drag tectonic plates along their surfaces. This movement is central to the theory of plate tectonics, developed in the mid-20th century and now foundational to geology. Without the temperature differences that drive these flows, Earth's surface would be geologically inert. In deeper regions near the boundary between the lower mantle and the outer core, the gradient steepens dramatically. Temperatures reach thousands of degrees Celsius, creating a stark contrast between the silicate mantle and the molten iron-nickel core. This intense thermal gradient fuels the geodynamic, the process by which Earth's magnetic field is generated. As hot, electrically conductive fluid moves within the outer core, it sets up complex flows that generate magnetic lines of force encircling the planet. This magnetic shield deflects solar wind and cosmic radiation, preserving the atmosphere and protecting life. Studying these gradients is a monumental task. Direct sampling is limited to a few miles of crust through boreholes like the Kola super-deep borehole in Russia or deep mine shafts in South Africa. To probe deeper, scientists rely on seismic wave studies, laboratory experiments that simulate high pressure and high temperature conditions, and sophisticated numerical models. Through these tools, they reconstruct a thermal map of Earth's interior, refining our understanding of how heat flows and where the boundaries of tectonic and magnetic behavior lie. The practical applications of this knowledge are vast. Geothermal energy, a renewable resource that taps into Earth's internal heat, depends on identifying regions with favorable thermal gradients. Earthquake prediction, mineral exploration, and even strategies for nuclear waste storage all hinge on a deep understanding of how temperature behaves beneath the crust. What emerges from this study is a vision of Earth not as a static rock, but as a thermodynamic system. A planet shaped and sustained by gradients of heat as much as by the force of gravity. These gradients have persisted for billions of years, and they continue to regulate the processes that make our world dynamic and habitable. And yet, Earth is not alone in harboring such thermal engines. Beyond our blue planet, across the cold reaches of the outer solar system, icy moons orbiting giant planets conceal mysteries of their own. Worlds where internal pressure and thermal gradients interact not with rock, but with ice and liquid water. Some of these frigid satellites may hold vast oceans beneath frozen crusts, warmed not by sunlight, but by internal forces. It is here that we turn next, to explore how pressure and heat combine beneath the icy shells of distant moons, and what those hidden seas may reveal about the possibility of life beyond Earth. In the intricate continuum of thermodynamic forces that shape the cosmos, few phenomena so vividly encapsulate the interplay of pressure, temperature, and density as the white dwarf. Emerging from the dramatic death throes of stars not massive enough to become neutron stars or black holes, white dwarfs are not simply remnants. They are the frozen echoes of stellar lifetimes, stabilized by one of the most exotic and unintuitive pressures in all of physics, electron degeneracy pressure. This invisible quantum force operates not in the classical realm of temperature and volume, but in the deeply probabilistic domain of quantum mechanics, where the identities of particles and the uncertainty of their positions define physical reality itself. White dwarfs originate when stars similar in mass to our Sun exhaust their nuclear fuel. Lacking the mass to trigger further fusion beyond helium, these stars shed their outer layers into space, forming elegant planetary nebulae. What remains is the dense hot core, a stellar ember composed mostly of carbon and oxygen. But without nuclear fusion to counteract the force of gravity, this core should collapse under its own immense weight. Instead, it reaches a state of equilibrium governed not by heat or radiation, but by the Pauli exclusion principle, a cornerstone of quantum theory that dictates that no two electrons can occupy the same quantum state simultaneously. As gravitational collapse attempts to compress the stellar matter further, electrons are forced into increasingly compact spaces, resisting further compression. This resistance creates electron degeneracy pressure, a purely quantum mechanical phenomenon that acts independently of temperature. This type of pressure has no classical analog, unlike gas pressure, which increases with heat, or radiation pressure, which is tied to photon emissions. Degeneracy pressure exists even at absolute zero. It arises from the limitations imposed by quantum uncertainty and the indistinguishability of particles. As electrons are squeezed closer together, their momentum increases, not from thermal agitation, but from their confinement in space, generating a pressure that halts gravitational collapse. This balancing act is delicate. A typical white dwarf may contain the mass of the Sun compressed into a volume similar to that of the Earth, resulting in average densities of hundreds of thousands of grams per cubic centimeter. The surface gravity of such an object is nearly 100,000 times that of Earth. A mere teaspoon of white dwarf material would weigh several tons. The structural integrity of such an object is not upheld by heat or molecular bonds, but by the intrinsic quantum properties of electrons. However, this equilibrium has its limits. There exists a theoretical boundary known as the Chandrasekhar limit, named after the Indian-American astrophysicist Subramanian Chandrasekhar, who first calculated it in the early 20th century. This limit, slightly above 1 1/3 times the mass of the Sun, represents the maximum mass a white dwarf can possess while still being supported by electron degeneracy pressure. Beyond this threshold, gravity overwhelms the quantum resistance of the electrons, and the white dwarf can collapse further, potentially becoming a neutron star or triggering a Type A supernova. These supernovae are not only violent ends for white dwarfs, but they also serve as standard candles, cosmic lighthouses, allowing astronomers to measure vast intergalactic distances and even trace the accelerated expansion of the universe. White dwarfs, though remnants, are not static relics. Over billions of years, they gradually cool and fade, radiating away their residual heat until they become cold. Dark black dwarfs. Yet, because the universe is not old enough for any white dwarf to have fully cooled into this state, black dwarfs remain hypothetical, ghosts of a far future still to come. Meanwhile, the observable white dwarfs, some of which are among the oldest objects in the Milky Way, offer critical insight into stellar life cycles, galactic evolution, and the behavior of matter under extreme conditions. As we explore white dwarfs more deeply, we begin to understand that degeneracy pressure is not unique to them. It reappears, though in different forms, in even more extreme stellar corpses. When white dwarfs exceed their mass limit and collapse, the electrons and protons may fuse into neutrons, leading to an even denser form of matter, governed by neutron degeneracy pressure. This naturally leads us to the next stage in this journey through cosmic pressure, the study of neutron stars and the almost inconceivable densities and gravitational forces that define them. The progression from white dwarfs, sustained by quantum degeneracy pressure, to neutron stars and black holes, reveals a universe where gravity persistently challenges the structural limits of matter. When gravity finally triumphs, creating an entity so dense that not even light can escape. It leaves behind not a tangible object, but a region defined by an invisible boundary, the event horizon. Yet, long before matter vanishes into this horizon, it undergoes a violent and radiant transformation. In the swirling chaos that surrounds a black hole, this region, known as the accretion disk, is not merely a feature of cosmic architecture. It is one of the hottest and most energetic phenomena in the known universe, where gravitational forces are so intense and frictions so extreme that temperatures soar to levels that rival stellar cores. An accretion disk forms when matter spirals inward toward a black hole, drawn by its immense gravitational pull. This matter, often gas, dust, and even fragments of stars, is not pulled straight in. Instead, due to the conservation of angular momentum, it whirls around the black hole, flattening into a rapidly rotating disk. As it orbits, each particle of infalling matter experiences drag and friction, not only against other particles, but also against intense magnetic fields and turbulent plasma currents. This frictional interaction converts gravitational potential energy into thermal energy, heating the disk to extraordinary temperatures. In the outer regions of the accretion disk, temperatures are already fierce, hot enough to ionize hydrogen and emit copious amounts of visible light and ultraviolet radiation. But as matter spirals closer to the event horizon, it accelerates, compresses, and heats to even more extreme levels. Near the innermost stable circular orbit, which marks the closest distance matter can orbit before plunging into the black hole, temperatures can reach millions of degrees. At these inner radii, the disk emits high-energy X-rays and even gamma rays. This emission provides astronomers with a critical window into black hole behavior, for while the black hole itself emits no light, its accretion disk blazes with radiation. These staggering temperatures are not uniform throughout the disk. Rather, they follow a radial temperature gradient, dropping off with increasing distance from the black hole. The precise distribution depends on multiple variables, including the mass of the black hole, the rate of accretion, the viscosity of the plasma, and the disk's geometry. Supermassive black holes at the centers of galaxies can generate massive accretion disks that stretch across light years and operate at slightly cooler but still luminous temperatures, while stellar mass black holes have more compact, ferocious disks where heat and X-ray output peak dramatically. Another key factor contributing to the thermal dynamics of accretion disks is magnetic turbulence, particularly from the magneto-rotational instability. This phenomenon occurs when weak magnetic fields within the disk amplify and destabilize, converting rotational energy into heat and creating turbulence that enhances angular momentum transport. This allows outer disk material to move inward, while pushing inner disk material further toward the black hole, feeding the accretion process and sustaining the disk's blistering temperatures. Some of the most extreme temperatures ever observed in space emerge from these disks, particularly in quasars, galactic nuclei powered by supermassive black holes. These objects can outshine entire galaxies due to their accretion disks, releasing energy equivalent to trillions of suns. Even in closer systems, like X-ray binaries, where a black hole feeds off a companion star, the accretion disk glows intensely in high-energy bands, betraying the presence of the otherwise invisible black hole. Radiation pressure in the innermost disk regions can become so intense that it begins to counteract gravitational pull, potentially stalling or even reversing accretion in certain cases. The delicate balance between radiation, gravity, and matter flow defines not only the thermal structure of the disk, but also its longevity and observational signature. In some systems, bursts of accretion cause transient outbursts, brief episodes of intense brightness, as large quantities of matter are consumed and heated, followed by periods of dormancy. Despite their violent energy output, accretion disks also serve as laboratories for testing fundamental physics, including the effects of general relativity in curved spacetime. Light emitted near the event horizon experiences gravitational redshift and time dilation, effects that have been measured and used to confirm the predictions of Einstein's equations. In fact, by analyzing the broadening of spectral lines from accretion disks, astrophysicists can determine the spin rate of black holes and infer their mass and angular momentum. And yet, as fierce as these accretion disks may be, they do not represent the end of a black hole's influence. In some cases, material in the inner disk is not consumed at all. Instead, it is redirected along the black hole's magnetic poles and launched into space as relativistic jets, narrow, high-speed streams of charged particles that extend for thousands or even millions of light-years. These jets, which radiate radio waves and X-rays, are among the most powerful features in the universe. Their origin lies in the very engine of the accretion disk, and their existence bridges the thermal dynamics of infalling matter with the explosive ejection of high-energy plasma into intergalactic space. Thus, the thermal extremes of accretion disks not only light up the surroundings of black holes, but also shape galactic evolution, power cosmic feedback mechanisms, and give rise to structures that influence matter on interstellar and even intergalactic scales. Yet, for all the energy released, for all the intense radiation emitted, there remains the ultimate mystery of what happens within the black hole itself. As we move inward past the disk, into the event horizon and toward the singularity, we reach a realm where current physics fails, a place where space and time collapse, and the known laws of thermodynamics, gravity, and quantum theory break down. This leads us into one of the most puzzling and contested arenas in modern science: the paradox of black hole entropy and the deeper meaning of information loss. Pressure effects on atmospheres of hot Jupiters. In the harsh furnace of proximity to their parent stars, the gas giants known as hot Jupiters exist in a realm of extreme physics and volatile chemistry. These massive planets, often larger than Jupiter, yet orbiting far closer to their stars than Mercury does to our Sun, represent one of the most dramatic examples of atmospheric transformation driven by pressure, heat, and radiation. Their atmospheric profiles offer a window into the interplay of gravitational compression, stellar radiation, and hydrodynamic forces that alter not only the chemical makeup of the atmosphere, but also its structure, density, and motion. The term hot Jupiter was coined following the unexpected discovery of the exoplanet 51 Pegasi b in the mid-1990s. This planet, with a mass similar to that of Jupiter, but orbiting its star in a matter of days, stunned astronomers and forced a reconsideration of planetary formation models. Unlike Jupiter, which lies deep within the solar system's colder outer reaches, hot Jupiters are forged or migrated to orbits that bring them so close to their stars that their atmospheres experience pressures and temperatures unlike anything in the solar system. At the core of their atmospheric dynamics is pressure, a variable dictated by both the planet's own gravity and the immense heating it undergoes due to stellar proximity. These planets are subject to constant irradiation, with the day side receiving thousands of times more solar energy than Jupiter does. The result is intense heating of the upper atmospheric layers, creating powerful thermal gradients that drive turbulent winds at thousands of miles per hour and lead to the expansion and inflation of the atmosphere itself. This expansion does not occur unchallenged. The planet's gravity seeks to compress and retain the outer gases, establishing a delicate and dynamic balance between thermal expansion and gravitational confinement. This tension gives rise to pressure structures that vary dramatically with altitude, latitude, and time of day. On the scorching day side, temperatures can soar above 3,000 degrees Fahrenheit, pushing the atmosphere outward, thinning its density and allowing it to interact directly with stellar radiation. On the cooler night side, pressure-driven downflows pull atmospheric gases inward, causing turbulent mixing and the redistribution of thermal energy. Such pressure-induced circulation plays a critical role in shaping the chemical profile of hot Jupiter atmospheres. High-energy photons from the host star ionize and dissociate molecules in the upper layers, creating a photochemical haze that absorbs and scatters light. At the same time, high pressures deeper within the atmosphere encourage recombination and the formation of complex molecules, including exotic metallic compounds and high-temperature clouds made of silicates or even iron. The extreme pressure gradients also influence cloud formation and vertical layering. Unlike Earth, where clouds are formed from water vapor condensing under mild pressure differences, hot Jupiters can form clouds composed of vaporized rock and metal that condense under conditions of intense compression. These clouds are not mere weather phenomena, they are key indicators of atmospheric evolution and energy transport, and they play a decisive role in the planet's albedo and thermal emission. In some cases, the pressure and heat become so overwhelming that the outer atmosphere escapes entirely. This phenomenon, known as atmospheric blow-off or hydrodynamic escape, is driven by the immense energy deposited by the star and facilitated by the relatively low gravitational binding at the planet's inflated outer layers. Ultraviolet radiation ionizes hydrogen atoms, heating the gas and creating an expanding envelope that can extend tens of thousands of miles into space. As the atmosphere expands beyond the Roche lobe, the region within which the planet's gravity dominates, it spills into interplanetary space, forming comet-like tails of gas detectable by ultraviolet and infrared telescopes. This escape process is not uniform. It is governed by a complex interaction between thermal pressure, radiation pressure, and the planet's magnetic field, if present. Some hot Jupiters may develop protective magnetospheres that channel and redirect escaping particles, while others are stripped more freely, losing mass at rates that can gradually erode the atmosphere over geological timescales. The degree of pressure confinement in the lower atmosphere thus becomes a key determinant of atmospheric longevity. Understanding the pressure-driven dynamics of hot Jupiter atmospheres has profound implications for the broader field of exoplanetary science. These planets serve as natural laboratories for studying atmospheric physics under extreme conditions, insights that can be extended to a wide variety of exoplanets, including smaller terrestrial worlds. Moreover, the pressure profiles inferred from transmission spectrum obtained as these planets pass in front of their stars reveal crucial information about atmospheric composition, cloud structure, and thermal gradients. As pressure sculpts the towering, windswept, and often unstable atmospheres of hot Jupiters, it connects to a wider narrative about the role of force and environment in planetary identity. These atmospheres are not static shells. They are living, evolving systems, shaped by deep interior physics and external radiation alike. And this brings us to another layer of complexity, one that pushes beyond the atmospheric shell and into the deeper internal regions of these gas giants and other worlds. What happens when pressures grow so immense that ordinary chemistry gives way to the unexpected? As we transition now from the external to the internal, we begin to explore an even more enigmatic frontier, the strange and extreme physics at play in high-pressure ice giants and planetary cores. In the next segment, we journey deeper into matter itself, confronting the exotic behaviors of degenerate states in ultra-dense worlds. The boiling and freezing points across alien worlds. As we drift farther from the blistering atmospheric pressure zones of hot Jupiters, where gas expands and escapes into space, we arrive at another crucial frontier of planetary science, one that is deceptively simple, yet extraordinarily complex. The boiling and freezing points of substances across alien worlds. On Earth, we are intimately familiar with the behavior of water. It freezes at 32 degrees Fahrenheit, boils at 212, and behaves in ways foundational to life, weather, and geology. But this neat system of phase changes exists only because of Earth's specific atmospheric pressure and temperature. Change the pressure, alter the gravity, introduce alien chemistry or exotic atmospheres, and the rules of boiling and freezing transform, sometimes across the cosmos. These transformations are not anomalies, they are the norm. The very notion of a boiling point is not a fixed quantity, it is a dynamic property that depends heavily on ambient pressure. On Earth, sea level pressure allows water to boil at what we define as normal. Climb a mountain, and the pressure drops, bringing the boiling point down with it. Travel to space, where the vacuum reigns, and water doesn't boil. It sublimates, passing instantly from solid to vapor. This fluid relationship between pressure and boiling is central to understanding the behavior of matter on other planets and moons. Take, for example, the icy surface of Europa, one of Jupiter's moons. There, water is not liquid, but rock-hard ice, hardened not merely by low temperature, but by a nearly non-existent atmospheric pressure. Any surface water exposed to the Jovian vacuum would boil and evaporate almost instantly, even though the surface temperature is frigid. The boiling point here is so low that it is essentially unattainable, meaning water cannot exist in liquid form without being trapped under ice or pressurized below the surface. This makes Europa's potential subsurface oceans all the more fascinating, as they exist in hidden chambers where internal pressure and heat allow water to stay liquid, defying the expectations set by the moon's icy crust. Contrast this with Titan, Saturn's mysterious moon, cloaked in a thick, nitrogen-rich atmosphere. Here, the pressure at the surface is higher than Earth's, and the temperatures hover hundreds of degrees below freezing. In this alien environment, methane and ethane take on the roles that water plays on Earth. They rain from orange clouds, carve river channels, and fill lakes. The freezing and boiling points of these hydrocarbons are such that they can remain liquid in Titan's surface conditions, creating a cycle similar to Earth's hydrological system, but based on entirely different substances. On Titan, methane freezes at temperatures far below those survivable by terrestrial life, and it boils at temperatures that would still be lethally cold to any Earthborn species. This reveals how fluid behavior is entirely contextual, tied to the chemistry of a world and its pressure-temperature profile. Then there is Venus, Earth's planetary twin in terms of size, but radically divergent in climate, with surface pressures more than 90 times that of Earth and temperatures high enough to melt lead. The boiling points of most substances are pushed upward dramatically. Water, even if it somehow reached the surface of Venus, would not survive. It would superheat into steam instantly and be destroyed by photodissociation in the upper atmosphere. Even metals like zinc or bismuth have their boiling points challenged by Venusian conditions. The combination of immense pressure and extreme temperature reshapes the phase behavior of virtually all known elements and compounds. Beyond our solar system, the rules continue to bend. On planets orbiting red dwarfs, where stellar radiation is intense but uneven, it's possible to find tidally locked planets, with one face perpetually scorched and the other in eternal shadow. On such a planet, the boiling and freezing points of the same substance could occur simultaneously within a span of just a few hundred miles. Imagine oceans frozen on one hemisphere and boiling violently on the other, driven solely by planetary orientation and the limited redistribution of heat through wind and oceanic currents. This duality forces us to redefine the very concept of a stable phase, something that seems immutable on Earth, but is profoundly fluid across the universe. There are also planets with ultra-low gravity, where atmospheric pressure is so weak that substances boil at near cryogenic temperatures, and where freezing points are essentially irrelevant because liquids cannot exist long enough to solidify. Such environments may favor the existence of exotic fluids, liquids composed of hydrogen, helium, or even silicates, that behave very differently under low gravity and low pressure conditions. These fluids often transition between phases in ways that do not even resemble the familiar liquid-gas model from Earth, but instead include supercritical phases, where distinctions between boiling and evaporation disappear altogether. Boiling and freezing also depend on atmospheric composition. A planet dominated by carbon dioxide, like Mars, has a freezing point for that gas at around -109 degrees Fahrenheit, allowing for seasonal frost deposits and dry ice clouds. But on Mars, water behaves chaotically. It freezes quickly and boils at relatively low temperatures because the atmosphere is so thin. As a result, stable liquid water is extremely rare, limited to momentary appearances in briny flows or deep subsurface aquifers where pressure can remain high enough to defy surface evaporation. As we explore exoplanets with atmospheres made of hydrogen sulfide, ammonia, or even vaporized metals, we must account for how these exotic gases shift phase boundaries. An atmosphere composed of sodium vapor might produce metallic rains under the right conditions, with freezing and boiling points that are utterly alien to terrestrial biology. Such atmospheres may even exist in temperature-pressure regimes where known chemistry begins to break down, where electron orbitals deform, and elements behave in ways not previously recorded. Furthermore, high-pressure environments, such as those found in the interiors of gas giants, cause familiar substances to take on unfamiliar forms. Under pressures of millions of atmospheres, hydrogen becomes metallic, a phase that does not occur naturally on Earth, but is predicted and now partially observed in lab conditions. In this state, boiling and freezing lose their traditional definitions, replaced by quantum mechanical transitions and phase boundaries that defy intuition. These metallic fluids may form oceans of liquid metal beneath the cloud tops of Jupiter or Saturn, changing our understanding of conductivity, magnetism, and planetary heat transfer. Thus, across the universe, boiling and freezing points are not simple thresholds, but fluid, context-driven phenomena shaped by pressure, temperature, chemical identity, gravity, and planetary evolution. They tell a deeper story about each world, not just what substances are present, but how those substances behave, move, interact, and transform under the forces that shape planetary environments. As we continue to investigate how matter behaves across such diverse alien landscapes, a new challenge emerges. How do we decode the structure of atmospheres and materials in places we cannot yet touch? How do we measure pressure, temperature, phase, and composition at thousands or even millions of miles away? The next part of our exploration delves into these remote sensing techniques and the intricate velocity fields that reveal the hidden dynamics of expanding galaxy clusters, where the movement of gas and dark matter plays a cosmic symphony written in pressure, gravity, and time. In the frozen frontiers of our solar system and beyond, there exists a geological phenomenon so alien, so quietly powerful, that it challenges our very definition of volcanic activity. Cryovolcanism, volcanoes that do not erupt molten rock, but instead expel volatile ices and liquids, represents a chapter of planetary science that pushes the boundaries of our understanding about what it means for a world to be geologically alive. Far from the incandescent calderas of Earth or the towering lava fountains of Jupiter's moon Io, cryovolcanoes operate under entirely different rules, governed not by fire and magma, but by extreme cold, pressure, and the strange physics of exotic ices. The term cryovolcano was first coined in the late 20th century, as planetary scientists began examining peculiar surface features on icy moons, such as Triton, Europa, and Enceladus. These worlds, orbiting gas giants in the cold outer reaches of the solar system, were once believed to be dormant, lifeless balls of frozen rock and ice. But data returned from Voyager, Galileo, and later Cassini spacecraft missions painted a radically different picture. One of tectonic cracking, resurfacing, and, most startlingly, eruptions of water, ammonia, and methane, in solid, liquid, or vapor form. Cryovolcanism begins deep below an icy crust, in a hidden interior warmed not by solar radiation but by tidal flexing. This process, driven by the gravitational tug-of-war between a moon and its parent planet, generates internal friction, creating enough heat to melt subsurface ice into pockets of briny, volatile-rich liquid. Over time, pressure builds within these chambers, eventually forcing the liquid upward through fractures in the crust. The result is an eruption, not of lava, but of cryomagma, which may consist of water mixed with other substances, like ammonia or methanol, that remain fluid at extremely low temperatures. Upon reaching the surface, this frigid slurry rapidly freezes, depositing smooth, icy plains, dome-like features, or ridged terrain. On Neptune's moon Triton, dark plumes rise from circular pits, thought to be geyser-like cryovolcanic vents. These eruptions are believed to be driven by seasonal heating from the distant sun, which warms a thin layer of frozen nitrogen beneath a translucent ice shell, triggering an explosive phase transition from solid to gas. The nitrogen bursts out, carrying dust particles that leave dark streaks across the surface. These observations suggest that, even with surface temperatures hovering near absolute zero, some level of active geology persists. Saturn's moon, Enceladus, offers perhaps the most compelling modern evidence of cryovolcanism. In 2005, NASA's Cassini spacecraft discovered towering jets of water vapor and ice particles spewing from fractures near the moon's south pole. These tiger stripes, as they're called, act like cryovolcanic geysers replenishing Saturn's earring and hinting at a vast subsurface ocean beneath Enceladus' icy crust. Spectral analysis of the plumes has revealed the presence of salts, silicates, and organic compounds, components that raise tantalizing possibilities for microbial life. The heat needed to maintain this activity likely comes from tidal interactions with Saturn, offering a powerful demonstration of how energy from orbital dynamics can drive internal heat on small icy worlds. Europa, one of Jupiter's largest moons, shows signs of a similar under-ice ocean, with surface ridges and chaos terrain suggesting that cryovolcanic processes have played a major role in reshaping the moon's landscape. Radar and magnetometer data support the theory that warm, briny water sometimes rises toward the surface, freezing into new terrain or potentially venting into space. While no active eruptions have been directly observed, future missions, such as NASA's Europa Clipper, aim to confirm whether cryovolcanism continues today, and, if so, what it reveals about the moon's interior and potential habitability. Beyond our solar system, the concept of cryovolcanism grows even more exotic. Exoplanets and exomoons orbiting cold, distant stars may host conditions ripe for icy volcanism on an even grander scale. For instance, a massive icy super-Earth with high internal pressures could harbor a thick mantle of exotic high-pressure ices like Ice X7 or Ice XX, with internal heat driving upward flows of water and volatiles. On such worlds, the cryomagma might consist of compounds alien to our planet, like liquid nitrogen or ethane, and erupt in bizarre forms dictated by extreme gravity and cold. Importantly, the study of cryovolcanism extends far beyond geological curiosity. These icy eruptions provide windows into planetary interiors that are otherwise inaccessible. By analyzing plume compositions and surface deposits, scientists can infer chemical processes occurring beneath the crust and assess the thermal evolution of these worlds. Cryovolcanoes may even serve as conduits for biological materials, transporting nutrients and possible microbes from subsurface oceans to the surface, or into space, where future landers and flybys might collect and analyze them. The mechanisms that enable cryovolcanism underscore a broader truth in planetary science, that heat, pressure and fluid dynamics operate in diverse and surprising ways across the cosmos. Volcanism, once thought the exclusive domain of molten rock and high temperatures, now encompasses a spectrum of processes adapted to the unique conditions of each world. In doing so, it bridges the gap between what we know of Earth and the broader mechanics of the universe. As we trace the glacial breath of cryovolcanoes across distant moons and frozen exoplanets, we are reminded that planetary activity takes many forms. Even in the outer solar system, where sunlight is weak and temperatures plunge, nature finds a way to reshape the surface, release internal energy, and perhaps even support life. From the ghostly plumes of Enceladus to the shadowed fractures of Europa, cryovolcanism invites us to rethink where and how geological vitality might emerge. This dynamic reality of frozen eruptions naturally leads to deeper questions about the atmospheric and surface conditions of these alien worlds, particularly the role of radiation and cosmic energy in influencing their evolution. To understand this interplay, we now turn to the next chapter in our cosmic journey, examining how intergalactic radiation permeates the universe and influences matter, energy, and planetary environments far beyond the warmth of any sun. Pressure-induced metallic hydrogen in Jupiter. Deep within Jupiter's immense atmosphere, beyond the turbulent storms, colorful belts, and fierce winds, lies a region of unimaginable pressure and exotic physics, a place where hydrogen, the simplest and most abundant element in the universe, is believed to transform into something extraordinary: a metallic state. This transformation, known as pressure-induced metallic hydrogen, stands as one of the most exotic and consequential processes in planetary science. It bridges chemistry and quantum physics, theory and experimentation, and carries profound implications for not just Jupiter's structure and magnetic field, but also for our understanding of high-pressure physics and even the early universe. To understand this phenomenon, we must begin by tracing the behavior of hydrogen under normal conditions. On Earth, hydrogen is a colorless, odorless gas made up of diatomic molecules. It is the lightest of all elements and the most abundant in the cosmos. But the hydrogen found in the dense core regions of Jupiter exists under pressures and temperatures that defy everyday experience. These are environments where atoms are compressed to such extremes that electrons are torn from their parent nuclei, creating a sea of charged particles, a metallic fluid capable of conducting electricity. This concept was first theorized in the early 20th century, not in the context of planets, but as a problem in high-pressure physics. Scientists such as Eugene Wigner and Hillard Bell Huntington proposed that hydrogen, if squeezed tightly enough, would abandon its molecular identity and behave like an alkali metal. This prediction remained theoretical for decades because reproducing the necessary pressures in a laboratory proved immensely difficult. It wasn't until advancements in diamond anvil cell technology, devices capable of generating pressures comparable to those inside gas giants, that researchers began to glimpse hydrogen's transformation. Even now, the creation and conformation of metallic hydrogen on Earth remain among the most controversial and elusive pursuits in experimental physics. Jupiter provides a natural crucible for this transformation. As a gas giant with a mass over 300 times that of Earth, Jupiter's interior pressure increases rapidly with depth. Beneath the cloud layers, the hydrogen becomes increasingly compressed and heated. At depths beyond several thousand kilometers, molecular hydrogen is predicted to dissociate into atomic hydrogen. Then, under pressures exceeding several million times Earth's atmospheric pressure, this atomic hydrogen is thought to undergo a phase transition into a metallic state. Unlike a solid metal, the metallic hydrogen in Jupiter is believed to exist as a dense liquid. Its free-moving electrons make it an excellent conductor of electricity. This property is essential to understanding one of Jupiter's most distinctive features: its powerful magnetic field. Jupiter's magnetic field is by far the strongest of any planet in the solar system, extending millions of miles into space and forming a massive magnetosphere This field is generated by a dynamo effect, similar to Earth's, but driven not by a core of molten iron, but by the swirling flows of metallic hydrogen deep within Jupiter's interior. The behavior of metallic hydrogen also influences Jupiter's internal heat. Despite being 5 times farther from the Sun than Earth, Jupiter radiates more energy than it receives. This excess heat is believed to come from the planet's slow gravitational contraction, a process called Kelvin-Helmholtz heating, and from energy released during the transition of hydrogen into its metallic phase. As hydrogen is compressed and rearranged, latent heat is released, contributing to the thermal budget of the planet. Moreover, the extent and depth of Jupiter's metallic hydrogen layer shape its internal dynamics and structure. Data from missions like Juno, which orbits Jupiter in a polar trajectory, have helped scientists model the gravitational field of the planet with unprecedented precision. These measurements suggest that the metallic hydrogen zone may extend over half the planet's radius, influencing not just magnetic activity, but also the zonal wind patterns observed at the surface. The implications of metallic hydrogen extend beyond Jupiter. Saturn, with its own deep hydrogen envelope, is also expected to harbour a metallic hydrogen layer, though likely thinner due to its smaller mass. The presence or absence of metallic hydrogen in exoplanets, especially those classified as hot Jupiters orbiting other stars, could determine whether they exhibit magnetic shielding, intense radiation belts, or auroras. Furthermore, understanding this exotic phase helps astrophysicists reconstruct the formation histories of gas giants, the processes at play in young planetary systems, and the early conditions of the solar nebula. Interestingly, if metallic hydrogen could ever be stabilized at surface pressures, a possibility still speculative, it might possess extraordinary properties, such as room temperature superconductivity. This has driven interest not only from planetary scientists, but also from material scientists and energy researchers. A material that could conduct electricity with zero resistance at room temperature would revolutionize energy transmission, magnetic levitation, and computational systems. Yet such possibilities remain firmly in the realm of theoretical projections until the extreme environments of Jupiter can be reproduced and controlled on Earth. The mystery of metallic hydrogen is thus a reminder of how the cosmos operates not just on immense spatial scales, but also on atomic ones. Deep inside a distant gas giant, the behavior of a single element, hydrogen, under the weight of planetary mass, reshapes our understanding of magnetism, heat, structure, and matter itself. And as we transition from the crushing depths of Jupiter's interior, where pressure transforms hydrogen into a metallic sea, we ascend again to explore the subtle temperatures that shape distant planets. For just as pressure alters states deep within, it also defines the limits of existence at the surface. We now turn to the thin boundaries where matter freezes and boils, across alien worlds where atmospheres are sparse, temperatures are strange, and the rules we take for granted on Earth are rewritten with every orbit. In the immense theatre of the Jovian system, where gravity sculpts moons into tortured, shifting landscapes, no celestial body is more violently alive than Io. This tiny, mottled moon, no larger than Earth's own satellite, is a world in perpetual agony, its surface rent open time and again by the explosive forces churning beneath. It is a world where lava lakes bubble and boil, not just as fleeting eruptions, but as enduring features of its geologic personality. The thermal dynamics of Io offer a vivid lens into planetary heat mechanics, tidal flexing, and the boundaries of volcanism beyond Earth. Io is the most volcanically active body in the solar system, a title it owes not to its size or composition alone, but to the relentless gravitational torture exerted by Jupiter and its neighbouring moons, Europa and Ganymede. These bodies participate in what's known as a Laplace resonance, a synchronized orbital dance that causes Io's path to periodically elongate, increasing the tidal forces it experiences. As Io's interior is pulled and compressed, frictional heat is generated deep within. Unlike Earth, where heat emerges slowly and sporadically, Io's heating is persistent and violent. The consequence is an interior perpetually under siege, with molten silicates constantly seeking escape through fractures and vents across its tortured crust. Among Io's most fascinating features are its lava lakes, immense molten basins that remain liquid not for hours or days, but for years, possibly centuries. Lurky Patera, the most famous of these, spans more than 100 miles across, dwarfing any terrestrial volcanic structure. What makes these lava lakes so remarkable is not just their size, but their dynamic behavior. Infrared observations have revealed periodic brightening events on Loki, suggesting cycles of crustal overturn. Essentially, the surface of the lake cools, forming a thin crust that eventually sinks under its own weight, allowing fresh lava to well up in its place. This pulsing activity is not random. It follows a thermal rhythm driven by Io's internal heat budget and the changing tidal stress imposed by Jupiter's gravity. The composition of Io's lava is equally compelling. Unlike the basaltic flows common on Earth, Io's lava is believed to be ultramafic, composed of magnesium-rich silicates that melt at temperatures well above 2,000 degrees Fahrenheit. These high temperatures make Io's eruptions more energetic and its lava more fluid. Plumes from some volcanic centers rise hundreds of miles into space, visible even from telescopes on Earth. These outbursts not only paint Io's surface with sulfur and silicate frost, but also feed Jupiter's vast magnetosphere with ionized particles, linking the Moon's fiery geology to the broader electromagnetic environment of the Jovian system. Io's thermal emissions have been a topic of intense scrutiny since the Voyager missions first unveiled its eruptive face in the late 20th century. Subsequent flybys by Galileo and New Horizons deepened our understanding, showing that Io's volcanic heat is not evenly distributed. Some regions radiate far more energy than others, indicating localized heat sources beneath the surface, possibly magma chambers or conduits aligned with fault zones. Recent observations using adaptive optics and space telescopes have begun to resolve surface details on a finer scale, allowing researchers to track heat flow patterns over time. These studies suggest that Io's volcanic power is both deeply rooted and constantly evolving, a testament to the intricate feedback loop between interior heat, crustal structure, and orbital dynamics. Despite its frenetic geological pace, Io also teaches us about stability in extremity. Its lava lakes do not simply erupt and vanish. They are systems, governed by physics as robust as those shaping Earth's continents. The thermal dynamics involved include convective overturn, radiative cooling, and phase transitions of silicate materials. These processes unfold in an environment where atmospheric pressure is negligible, meaning boiling and solidification occur under vastly different rules than on Earth. Lava here may degas differently, spread more thinly, and cool in bizarre patterns dictated by vacuum exposure and rapid sublimation of surface compounds. Moreover, Leo's intense volcanism gives rise to a tenuous atmosphere primarily composed of sulfur dioxide, which condenses onto the surface during its long eclipse periods when the Moon slips into Jupiter's shadow. As sunlight returns, this frozen gas resublimates, creating brief cycles of atmospheric rebirth. These changes in surface pressure feed back into the thermal dynamics, influencing heat loss, eruption vigor, and lava lake behavior. The entire system is a masterclass in extreme planetary physics, where geology, thermodynamics, orbital mechanics, and chemistry collide in relentless chaos. Beyond the spectacle, Io serves as a laboratory for understanding volcanic processes across the cosmos. Its lava lakes are analogues for those potentially hiding beneath the ice of Europa or simmering on the scorched surface of exoplanets orbiting red dwarfs. Its tidal heating mechanism offers a template for thermal evolution in compact planetary systems where gravitational interactions dominate internal energy budgets, and its constant flux reminds us that not all worlds grow cold with age. Some, like Io, remain youthfully destructive, defying the cosmic norm of entropy. As we continue to explore this molten moon, future missions may one day deploy orbiters or landers capable of observing Io's lava lakes in real time, measuring their heat flux, seismic activity, and composition with unmatched precision. In doing so, we may not only decode the furious heart of this tiny world, but also extend our understanding of where heat and life might coexist across the universe. The fires of Io, while alien, burn with principles that are universal, reminding us that even in the farthest reaches of the solar system, the dance of pressure, temperature, and time is eternal. And as we descend from the glowing infernos of Io to the frigid shadows of the outer solar system, we now turn our attention to a darker and far more mysterious landscape where the remnants of massive stellar explosions cast silent echoes through space. In the next chapter, we explore the ancient aftermath of supernovae, peeling back the layers of cosmic dust and radiation to uncover the legacy of stellar death and how it continues to shape the galaxies around us. Beneath the frozen crusts of the outer solar system's most enigmatic moons, a hidden world stirs. These are the icy moons: Europa, Enceladus, Ganymede, Titan, and unlike barren, crater-pocked surfaces of many celestial bodies, these frozen satellites may harbor something profoundly Earth-like: oceans. But not oceans warmed by sunlit skies or tidal breezes. These are dark, pressurized seas encased beneath miles of ice, locked away from starlight and powered by alien forces. The story of these subsurface oceans is one of unimaginable pressure, exotic chemistry, and the relentless influence of gravitational energy. At first glance, these moons appear desolate. Europa, the smallest of Jupiter's 4 Galilean moons, is a ball of cracked ice streaked with long reddish scars. Enceladus, orbiting Saturn, gleams with a brilliant white shell, constantly replenished by jets of icy vapor from its south pole. Ganymede, the largest moon in the solar system, even larger than Mercury, bears grooves and ridges hinting at inner movement. Titan, thick with an opaque orange haze, hides not only liquid methane lakes on its surface, but likely a water ocean far below. Despite their differences, these worlds share one trait. Their frozen exteriors are mere covers for deep, dark, and pressurized oceans beneath. But how do oceans exist so far from the sun in regions where surface temperatures hover hundreds of degrees below freezing? The answer lies in pressure and tidal heating. Unlike Earth, where sunlight drives the water cycle, these moons rely on the immense gravitational forces of their parent planets. As they orbit, they are flexed and squeezed by tidal forces. This frictional kneading heats their interiors, much like how bending a paperclip repeatedly can make it warm. Over time, this heat melts interior ice, forming global oceans beneath crusts of frozen shell. The pressures in these subsurface oceans are staggering. Europa's ocean, estimated to lie beneath 10 to 15 miles of ice, could reach depths of over 60 miles. The sheer weight of such an ice ceiling compresses the water below, raising its pressure to levels beyond any earthly sea. On Ganymede, where the ice shell may reach hundreds of miles thick, water may be sandwiched between multiple ice layers, each with different crystalline structures. Some exotic, such as Ice 6 or Ice 7, which only form under extreme pressure. These phases of ice, unfamiliar to human experience, are denser than the water itself and act as insulating barriers between the ocean and the moon's rocky core. This stratification leads to a critical question. What role does pressure play in sustaining or suppressing life? On Earth, hydrothermal vents at the bottom of the ocean support entire ecosystems, thriving without sunlight, powered by chemical energy from deep-sea volcanic activity. If similar hydrothermal systems exist on the seafloors of Europa or Enceladus, pressure could concentrate vital chemicals like hydrogen sulfide and methane, enabling life to emerge. But at the same time, high pressure changes water's physical properties, altering viscosity, density, and how molecules behave, possibly shaping life in ways completely unknown to Earth biology. Chemical interactions at such depths are equally intriguing. As pressures rise, molecules like ammonia and salt act as antifreeze, lowering the freezing point of water and allowing oceans to remain liquid even in the coldest environments. These compounds are not just contaminants, they are facilitators of liquid water under alien conditions. On Titan, where the surface teems with methane and ethane, the pressure in its deep ocean could dissolve these hydrocarbons into the water, creating an otherworldly cocktail of chemistry. The interface between water and rock at the ocean's base could lead to serpentinization reactions, releasing hydrogen gas, an essential energy source for microbial life. Then there are the geysers, plumes of water vapor erupting into space. On Enceladus, these icy jets burst from fractures in the crust called tiger stripes. Through these plumes, we have tasted the ocean without drilling a single hole. NASA's Cassini mission flew through them and detected salty water, organic molecules, and even signs of hydrothermal activity. These are not just curiosities, they are portals into hidden oceans, enabling scientists to study these environments. Remote pressure here is the gatekeeper, both enabling the ocean's existence and powering the geysers that break through to space. Yet, with all the data we have, so many questions remain. Could these oceans be long-living or fleeting? Is the pressure sustainable for billions of years, or will freezing eventually triumph? And, most profoundly, could evolution thrive in such alien pressure cookers? Scientists speculate that if life does exist on these moons, it might resemble deep-sea extremophiles on Earth. Organisms that flourish under high pressure in complete darkness with no photosynthesis at all. But evolution in these settings may have taken paths completely divergent from anything earthly, shaped by pressure, not light. As missions like Europa Clipper and Dragonfly prepare to explore these icy moons, understanding pressure's influence is vital. Whether it's the thickness of the ice, the chemistry of the sea, or the presence of life, pressure defines what is possible beneath these frozen shells. It is the invisible force sculpting not only the geology but also the biology of distant worlds. And just as pressure carves out deep oceans beneath icy mantles, it also affects the vast skies above, gas giants and hot Jupiters, where atmospheres swell and shrink, compress and expand under heat and gravity. In those blazing skies, another form of pressure reigns, not the crushing weight of ice, but the expansive violence of gas and plasma. From the oceanic depths of moons, we now ascend toward the turbulent, blistering skies of exoplanets, where pressure reshapes not seas, but the very atmosphere itself. The temperature-pressure balance that enables life. In the quiet crucible of space, life is not a given. It is a miracle of precision, an interplay of physical forces and chemical thresholds that must align just right. At the heart of this fine-tuned balance lies a powerful relationship, one that binds the most fundamental qualities of a planet or moon together: temperature and pressure. Their union determines the presence of liquid water, the stability of complex molecules, the nature of atmospheric circulation, and ultimately, the viability of life as we know it. On Earth, this relationship is elegantly poised. Atmospheric pressure at sea level keeps water in its liquid state across a range of temperatures, while Earth's distance from the Sun ensures that thermal conditions hover within a narrow band that allows biochemical processes to flourish. But this comfort zone, known as the habitable zone, is not solely about distance from a star. It is just as much about the gravity-induced pressure at the surface and how that pressure interacts with thermal conditions to maintain stability in matter, especially the presence of liquid solvents like water or methane. Pressure, derived from both gravity and atmospheric mass, plays a foundational role in whether a planet can retain a stable atmosphere at all. A thin atmosphere like that of Mars provides little insulation and fails to maintain surface temperatures that could support liquid water. Even though Mars once had flowing rivers and standing lakes, its inability to hold onto its atmosphere due to weak gravity ultimately made it cold and dry. This underscores how a delicate shortfall in pressure can render even a planet within the habitable zone inhospitable. Temperature alone does not suffice. On Titan, Saturn's moon, there is atmospheric pressure high enough to support surface liquids. However, due to its great distance from the Sun, those liquids are not water but methane and ethane, substances that remain liquid at much lower temperatures. Here, life may not follow Earth's recipe, but it reminds us that different chemical systems might operate under alternative balances of temperature and pressure. The same pressure that freezes water into lifeless ice on Titan could keep methane fluid and dynamic, offering the tantalizing possibility of exotic life based on alien chemistries. In contrast, Venus exhibits how too much pressure combined with excessive temperature becomes destructive. Its dense carbon dioxide atmosphere traps heat via a runaway greenhouse effect, pushing surface temperatures high enough to melt lead. The crushing atmospheric pressure, over 90 times that of Earth, further amplifies thermal effects, creating a furnace where no known biochemical system could survive. Yet, even in this extreme, researchers have speculated about microbial life in the more temperate cloud layers, where temperature and pressure might briefly mimic those of Earth's lower atmosphere. The influence of pressure extends deep into planetary interiors. On ocean worlds such as Europa and Enceladus, subsurface oceans are believed to exist beneath layers of ice, kept in a liquid state by internal heat and insulated by overlying pressure. These environments are entirely cut off from solar energy, but pressure-induced warmth from tidal flexing may provide enough energy to sustain chemical gradients, possibly mimicking the hydrothermal vents on Earth's ocean floors where life likely began. Such settings challenge the traditional definitions of habitability and extend the search for life to places once dismissed as too cold or too isolated. In the context of exoplanets, this balance becomes even more critical. Astronomers now analyze not just the size and orbit of exoplanets, but also clues about their atmospheres, pressures, and temperatures to judge whether they could host life. Super-Earths and mini-Neptunes blur the boundaries between rocky and gaseous worlds, and their surface conditions may vary wildly. On these distant planets, astronomers rely on models that simulate how pressure and temperature interact to support or destroy the conditions for habitability. Even in the lab, scientists replicate this balance. High-pressure chambers and thermal vacuums are used to test spacecraft components and simulate alien environments. These tests provide insight into the physical behaviors of matter under extraterrestrial conditions, helping us understand not just engineering challenges, but also where life might persist. Temperature and pressure are not merely abstract variables. They are the invisible architects of planetary identity. They dictate whether oceans can exist, whether atmospheres can hold together, whether molecules can form and survive. They influence weather, chemistry, and the potential for ecosystems in every extreme environment explored, be it a lava lake on Io, a cryovolcano on Triton, or a metallic hydrogen core within Jupiter. These two forces are the gatekeepers of possibility. Our journey through the cosmos has uncovered an astonishing variety of worlds, each sculpted by different regimes of temperature and pressure. From the boiling points on Venus to the frozen plains of Pluto, from methane lakes to buried oceans, and from collapsing gas giants to emerging exoplanets. This balance defines where life may take root or never begin at all. As we conclude this sweeping exploration across solar systems, we return to a humbling truth. Life is not a universal inevitability. It is the result of an exquisite harmony between heat and pressure, energy and matter, chaos and equilibrium. Understanding this interplay not only informs our search for life beyond Earth, it deepens our appreciation for the fragile balance that sustains life right here on our own precious blue world. Tidal galaxies, twisted by gravity. In the vast, cold architecture of the universe, galaxies are not the isolated islands we once believed them to be. They are wanderers in a sea of gravitational tides, drawn toward one another in slow, majestic dances that can last for billions of years. These cosmic encounters leave behind breathtaking relics, tidal galaxies contorted and stretched by the overwhelming force of gravity. These galactic forms are not merely visual spectacles. They are deep records of the universe's dynamism, violence, and continuous creation. Tidal galaxies emerge from gravitational interactions between massive galaxies. Unlike the serene spirals we often imagine when thinking of galaxies, tidal galaxies wear the scars of cosmic battles. When two or more galaxies come close enough, their mutual gravitational pull begins to tug at their outer stars, clouds of gas and dark matter. These tugs do not happen instantly, but unfold over millions or even billions of years. Stars are flung into tidal tails, enormous thread-like streams of stellar material, stretching across intergalactic space, sometimes forming arcs that span hundreds of thousands of light-years. The first clues to the existence of tidal galaxies came in the mid-20th century with improvements in photographic plate sensitivity and telescope optics. Astronomers began noticing peculiar galaxy shapes, twisted, stretched, and bent structures that defied classical spiral or elliptical categorization. The classic pair, known as the Antennae Galaxies, is one of the most iconic examples. Located in the constellation Corvus, this duo appears to be locked in a slow magmatic collision, their stars flung outward in brilliant arcs that resemble insect antennae. These trails are not static. They evolve, merge, and sometimes collapse into new structures altogether. But the wonder of tidal galaxies lies not only in their forms, but in what they teach us about galactic evolution. These interactions often trigger immense waves of star formation. As gas clouds are compressed by gravitational forces and shock waves, they collapse under their own weight, igniting bursts of newborn stars. Some of the most vibrant stellar nurseries ever observed are found in the heart of tidal interactions. Yet this creation often comes with destruction. Galactic cores may be destabilized. Supermassive black holes can begin to consume more matter, and entire structural features of galaxies may be torn apart, never to reform. From a scientific perspective, tidal galaxies offer an exceptional opportunity to study the role of gravity not just as a force of attraction, but as an agent of transformation. Simulations and models of galaxy collisions have revealed that these events are not rare. In fact, the Milky Way itself is not immune. Our home galaxy is on a collision course with the Andromeda Galaxy, a celestial ballet expected to begin in earnest in about 4 billion years. Already, satellite galaxies like the Large and Small Magellanic Clouds are stirring up tidal features in the Milky Way's halo, subtle arcs of stars and gas that hint at the beginning of a grand merger. These future tidal features will reshape the Milky Way, giving rise to yet another generation of twisted, luminous structures. Even the dark matter component of galaxies plays a crucial role in shaping tidal galaxies. Though invisible, dark matter contributes the majority of mass in most galaxies, forming vast halos that extend far beyond the visible stars. During a galactic encounter, these dark matter halos interact gravitationally as well, guiding the overall shape and trajectory of the tidal structures. Without dark matter, tidal interactions would look radically different. Less organized, less elongated, and lacking the coherence we observe. Thus, tidal galaxies serve as a silent testimony to the dark scaffolding of the universe. Beyond their scientific importance, tidal galaxies also carry philosophical weight. They remind us that beauty often comes from struggle, and that creation is frequently born from conflict. They are visual metaphors for resilience and transformation, telling a story of cosmic resilience and rebirth. Through their tortured shapes, we see the universe not as a static machine, but as a living, evolving organism, one that tears itself apart and builds anew, cycle after cycle. Yet even these grand tidal features are temporary. Over vast stretches of time, the dramatic tails and bridges will fade, stars will disperse into the larger galactic halos, and the memory of the collision will be lost, save for the newly merged galaxy at its center. These tidal ghosts are fleeting moments in the infinite film of cosmic evolution, captured only briefly by human eyes and instruments before they vanish into the background of space. As we observe these twisting galactic forms, we are not only looking outward, but forward. They are glimpses into the eventual fate of all galaxies, including our own. In their chaotic grace, tidal galaxies are both messengers of history and harbingers of what is to come. And with that glance into future galactic collisions and their inevitable consequences, we turn our attention to a stranger cosmic choreography, one that transcends even the most dramatic galaxy mergers. Next, we step into the realm of Outline 12, where we explore the bizarre and captivating world of ring galaxies, formed not by gradual spiral evolution, but by violent head-on collisions that send ripples through galactic disks like stones cast into a still. The Hercules Corona Borealis, Great Wall, the largest structure in the universe. As we leave behind the intricate gravitational dances that twist galaxies into tidal forms, our perspective must widen, not just across space, but across the very concept of scale itself. From the delicate, luminous threads spun by merging galaxies, we now move into a realm so vast, so profoundly immense, that it challenges the very boundaries of human comprehension. We arrive at what may be the largest known structure in the observable universe, the Hercules Corona Borealis Great Wall, a name as colossal as the cosmic giant it represents. Discovered in the early years of the 21st century, this immense superstructure came into view not through visible light or classical imaging, but through the detection of gamma-ray bursts, brief, high-energy flashes of radiation that typically signal the collapse of massive stars or the violent mergers of neutron stars. Astronomers analyzing data from deep sky surveys noticed a peculiar concentration of these bursts in a specific region of the sky, a statistical clustering too significant to be coincidental. The distribution pointed to a massive assembly of galaxies and galaxy clusters stretching across a truly unimaginable expanse, billions of light-years in length. The Hercules Corona Borealis Great Wall spans a region of sky that connects the constellations of Hercules and Corona Borealis, hence its name. The dimensions of this structure are staggering, over 10 billion light-years across at its greatest extent. To put this in context, our entire Milky Way galaxy is roughly 100,000 light-years in diameter. The Great Wall dwarfs not only our galaxy, but entire supercluster of galaxies, swallowing them like islands in a galactic ocean. It is not a wall in the traditional sense, but rather a vast web of gravitationally associated matter. Galaxies, dark matter, intergalactic gas, all interconnected in a filamentary structure that traces the skeleton of the cosmos. This raises a profound problem. According to the cosmological principle, the foundational idea in modern astrophysics that the universe is homogeneous and isotropic at sufficiently large scales, structures larger than about 1 billion light-years should not exist. The Hercules Corona Borealis Great Wall breaks that rule. It defies the expected limits of cosmic structure formation, posing a direct challenge to prevailing models of the early universe and the evolution of large-scale structure. If such a massive complex exists, how did it form within the age of the universe, and what unknown mechanisms might have guided its growth? Some scientists suggest that the wall could be a projection effect, or perhaps several smaller structures merely aligned along our line of sight. But deeper studies, cross-examined across wavelengths and time, continue to strengthen the case for its authenticity. If confirmed, the Hercules Corona Borealis Great Wall forces us to reimagine how matter organizes itself on the grandest scales. It may imply that the early universe had greater density fluctuations than our current models account for, or that gravitational clustering is more efficient across cosmic timescales than previously thought. This structure is part of a broader cosmic web, a vast interconnected lattice of filaments, voids, and nodes that define the very texture of the universe. Galaxies are not sprinkled evenly across space. Instead, they are found in thread-like formations, with vast empty regions in between. These threads converge in knots known as galaxy clusters, and the clusters themselves connect into larger assemblies called superclusters. The Great Wall may be the most extreme example of this arrangement, a kind of cosmic superhighway, where gravity has drawn together matter over distances that stagger the imagination. But the Great Wall is not just about scale. It also forces us to confront questions about the nature of the universe itself. If our cosmological assumptions are incorrect, what else might we be missing? Could there be even larger structures beyond our observational horizon? Or is the universe not as uniform as we once believed? The possibility that the cosmos harbors such immense, coherent formations adds fuel to discussions about anisotropies in the cosmic microwave background, alternative models of inflation, and even multiverse theories. Moreover, the Hercules Corona Borealis Great Wall reveals the extraordinary power of invisible forces in shaping the visible universe. Dark matter, unseen but gravitationally dominant, likely forms the backbone of this superstructure. Though we cannot see it directly, its influence is everywhere, guiding the motion of galaxies and sculpting the very architecture of space. In this way, the Great Wall becomes not only a structure of light and matter, but also a monument to the unseen, a cosmic fingerprint left by forces we still struggle to define. Even our ability to detect such a structure is a triumph of human ingenuity. The technology required to observe gamma-ray bursts across billions of light-years, to map their distribution, and to infer the existence of such a structure is itself the result of generations of scientific progress. From orbiting observatories to global data-sharing networks, the discovery of the Great Wall is a testament to how far humanity has reached into the deep night of space. And yet, as vast as it is, the Hercules Corona Borealis Great Wall may not be the final frontier of cosmic structure. As our instruments improve and our theories evolve, we may discover other megastructures, richer webs, longer filaments, deeper voids, stretching across space like neural pathways in a cosmic mind. And that idea, strange and poetic as it sounds, leads us to our next domain of wonder. For if the large-scale structure of the universe resembles a neural network, if it operates like an interconnected web, then it invites an even more profound question. Could the universe itself be conscious? Or does it possess some deeper logic that echoes the patterns of thought, memory, and awareness? As we journey forward into Outline 13, we shall confront the enigmatic frontier of cosmic consciousness, where physics meets philosophy and where science begins to question the nature of perception, sentience, and the very architecture of reality itself. Starburst galaxies, galaxies on fire. From the colossal stillness of the Hercules Corona Borealis Great Wall, where cosmic architecture unfolds on a scale that mocks our sense of proportion, we now plunge back into more intimate, but no less dramatic arenas of galactic life. If the Great Wall revealed the structure of the universe in skeletal form, then starburst galaxies represent its beating heart. Galaxies in a phase of violent, feverish transformation, igniting stars at a rate so furious that their entire evolutionary trajectory is altered. These are galaxies on fire, not with literal flames, but with the incandescent heat of explosive creation. A starburst galaxy is a galaxy caught in the throes of intense star formation, producing new stars at rates that can be dozens or even hundreds of times higher than those of ordinary galaxies. This frenzy of stellar birth is not a steady process, but a dramatic episode, a relatively short-lived surge in activity, often triggered by a specific catalyst. In astronomical terms, these starbursts are brief flashes of light and energy, often lasting only tens of millions of years, a blink of time compared to a galaxy's total lifespan, which typically stretches across billions of years. The triggers for starburst phases are as varied as they are violent. Galactic collisions, tidal interactions, and even internal gravitational instabilities can funnel vast quantities of cold gas into the central regions of a galaxy, collapsing it under its own weight. When this gas compresses rapidly, it creates the perfect conditions for star formation on a massive scale. Shock waves from previous supernovae, spiral density waves, or the gravitational tug of a passing satellite galaxy can all act as catalysts. The result is a firestorm of stellar birth, an astronomical version of a population explosion, where thousands of stars are born every year in tightly packed regions. One of the most studied starburst galaxies is Messier 82, also known as the Cigar Galaxy. Located in the constellation Ursa Major, it has become a cosmic laboratory for understanding the mechanics of starbursts. At its core, Messier 82 churns out stars at such an accelerated pace that its central regions glow with radiation, wind, and heat. Observations have revealed superwinds, enormous outflows of gas, driven by the combined energy of young stars, stellar winds, and supernovae blasting material out into intergalactic space. These superwinds can stretch for tens of thousands of light years, carrying not just gas but also heavy elements forged in the hearts of stars. The consequences of a starburst are profound and far-reaching. First, the sheer number of new stars changes the galaxy's structure and composition. Massive stars, which burn quickly and die young, explode as supernovae, enriching the surrounding space with metals like iron, calcium, and oxygen. These elements are essential for the formation of planets, moons, and life as we know it. In a sense, starburst galaxies are not only creating stars, but also seeding the future building blocks of life across the cosmos. Second, the energy released during a starburst can alter the galaxy's future. The supernovae and stellar winds inject so much momentum into the surrounding gas that it can halt further star formation or even eject gas entirely from the galaxy. This process, known as feedback, creates a self-regulating mechanism. A galaxy can only sustain a starburst for so long before it depletes its gas reserves or blows them out into space. Thus, the same process that ignites star birth can also extinguish it, leaving behind a quieter, more stable system. Or sometimes a galaxy stripped of its fuel, unable to form stars for eons. There is also a deeper cosmological importance to these luminous bursts of creation. Starburst galaxies are more common in the early universe, where galaxy interactions and mergers were frequent. Studying them allows astronomers to peer backward in time, understanding how the first galaxies evolved, how heavy elements were distributed, and how large-scale structures formed. Starbursts may even be connected to the emergence of quasars, those brilliantly bright, black hole-powered beacons that shine across the deep past. In some cases, the same galactic collisions that trigger a starburst also feed the central black hole, setting off a chain reaction of cosmic activity that transforms the galaxy entirely. And beyond science, there is something undeniably poetic about starburst galaxies. They are the very embodiment of cosmic urgency, a blaze of life in the cold darkness of space. They speak to us about energy, transformation, and the delicate balance between growth and destruction. In their glowing cores and radiating winds, they offer a glimpse of the universe at its most active and alive, showing us that galaxies are not static ornaments, but dynamic entities shaped by pressure, momentum, and the relentless pulse of birth and death. Even their infrared and radio signatures tell a story. Much of their activity is obscured by dust, hidden from visible light, but revealed in other wavelengths. This makes starburst galaxies prime targets for observatories like the James Webb Space Telescope, which can peer into these dust-shrouded regions to reveal the tangled dance of stars being born amid clouds of gas. In doing so, we not only witness the inner workings of starburst galaxies, but also refine our understanding of stellar life cycles, galactic evolution, and the chemical heritage of the universe itself. And as we leave behind these luminous furnaces of creation, we are once again drawn toward mystery, toward that other side of galactic behavior that does not involve bursts of activity, but rather silence, decay, and disappearance. The universe, in all its grandeur, is not only a place of expansion and birth, it is also home to fading light, to celestial phenomena that whisper of ends rather than beginnings. And so, as we transition forward, we enter the domain of Outline 14, where we will explore the enigmatic nature of dark galaxies, galaxies without stars, invisible to ordinary observation, yet teeming with dark matter and hidden potential, veiled in the silence of the cosmic void. Intergalactic stars, the loneliest wanderers in the cosmos. As we depart the heart of starburst galaxies, those luminous engines of creation, we are drawn toward a far more solitary and silent region of the universe. It is a realm not defined by frenetic birth or gravitational clashes, but by isolation, motion, and mystery. Here, between the vast gulfs that separate galaxies, travel stars that belong to no stellar city, no spiral arm, no galactic nucleus, these are the intergalactic stars, often called rogue stars, celestial exiles drifting through the dark vacuum between galaxies, untethered and alone. To understand the profound nature of these wandering stars, we must first grasp the environment they inhabit. The space between galaxies, known as the intergalactic medium, is vast and almost unimaginably empty. In these regions, the density of matter is so low that even light takes millions of years to travel between recognizable landmarks. Yet, scattered across this cosmic void are stars that shine, burn, and age like their galactic cousins. But with one critical difference: they do so in isolation. The existence of intergalactic stars was first proposed as a theoretical consequence of galactic interactions. When two galaxies collide or pass closely by one another, The powerful gravitational forces involved can fling stars out of their home systems. These ejected stars are accelerated to such high velocities that they escaped the gravitational pull of both galaxies, hurtling outward into the intergalactic abyss. This process is not random chaos. It is governed by the elegant laws of orbital mechanics and the conservation of momentum. The most common mechanism involves gravitational slingshots, where stars near the core of a merging system are caught in the complex ballet of colliding tidal forces and flung outward with enough energy to break free from their galaxy's embrace. Observational confirmation came slowly, due in large part to the difficulty of detecting stars in deep space without the background glow of a galaxy. But with the advancement of deep-field telescopes and instruments sensitive to faint light sources, astronomers began to identify luminous points floating between galaxies in clusters like Virgo and Coma. These stars, many of them red giants and supergiants, were too far from any galaxy to be bound to one, and their spatial distribution made clear that they were not mere statistical outliers. Instead, they represented a population of stars that had been torn from their homes and scattered across the intergalactic medium. The implications of these stars extend far beyond their unusual positions. Intergalactic stars act as tracers, natural probes that help map the gravitational and structural dynamics of galaxy clusters. Their distribution can reveal the history of past mergers, the mass distribution of dark matter halos, and the violent processes that have shaped the architecture of the universe. They are, in a sense, the fossils of cosmic violence, silent witnesses to events that unfolded over billions of years. Moreover, these stars challenge our understanding of stellar evolution in isolated environments. Most stars live within galaxies, where interstellar gas, magnetic fields, and stellar neighbors influence their formation, movement, and eventual death. But intergalactic stars exist largely without these interactions. They are solitary in the truest sense, evolving without the feedback mechanisms that govern galactic stellar populations. This isolation could lead to subtle differences in their lifespans, rotation rates, or end-of-life behavior. Differences that are still being studied and debated by astrophysicists. Some of these rogue stars are hypervelocity stars, traveling at speeds so extreme that they were likely ejected not just by merging galaxies, but by interactions with supermassive black holes. When a binary star system strays too close to such a black hole, tidal forces can rip it apart, flinging one star into intergalactic space while the other is devoured. These events produce some of the fastest objects in the universe and demonstrate the raw, destructive power of galactic core. Even more intriguing is the possibility that some intergalactic stars carry with them planetary systems, entire solar systems cast adrift in the cold dark. These potential rogue planets, orbiting stars far from any galaxy, might harbor moons, atmospheres, or even the elemental ingredients of life, all while flying through a universe that offers no nearby suns, no galactic context, and no celestial neighborhood. While purely speculative for now, the existence of such orphaned worlds poses deep philosophical questions about life's resilience and its possible emergence in environments we have barely begun to understand. Intergalactic stars also hint at the broader fate of galaxies and cosmic evolution. As galaxies merge and evolve, as stars are ejected and redistributed, the boundaries between what we call a galaxy and what lies outside it become blurred. Over cosmic timescales, stars leaking from galactic halos could form vast intergalactic stellar bridges, or clouds, challenging our definitions of structure and membership in the universe. The line between galaxy and intergalactic space is more porous than once believed. These lonely travelers, though few compared to the vast populations housed within galaxies, carry with them the stories of upheaval, acceleration, and exile. They shine against a backdrop of emptiness, reminding us that even in the most desolate reaches of space, stars still burn, life still pulses, and history continues to unfold. They offer us a unique lens, one not centered on belonging, but on freedom, motion, and the far-flung consequences of cosmic evolution. And just as these solitary stars illuminate the darkness between galaxies, they guide us toward another elusive phenomenon that inhabits the threshold of the observable and the theoretical. As we follow their trail further into the cosmos, we encounter not visible stars or known matter, but something far more mysterious and paradoxical: galactic systems that seem to contain no stars at all. In Outline 15, we delve into the strange, silent world of dark galaxies, invisible structures of hydrogen and dark matter that defy direct observation, yet may hold the keys to understanding how galaxies form, how matter assembles, and how much of the universe remains unseen. Dark galaxies, the invisible engines of the cosmos, as the glowing exiles of space. The intergalactic stars drift through the cosmic void in solitude. They reveal the aftermath of galactic upheaval and the dynamic violence that can unbind a star from its origin. But now we turn toward a stranger silence, not the quiet of isolation, but the absence of light itself. We descend into the shadows of the universe, seeking entities so elusive they cannot be seen. Yet their gravitational fingerprints mark their presence. These are the dark galaxies, structures composed almost entirely of invisible matter and gas, nearly devoid of stars and nearly undetectable by conventional observation. They are the missing pieces in our cosmic puzzle, the phantom frameworks on which the luminous universe is built. The notion of a galaxy without stars seems almost contradictory. For centuries, our understanding of galaxies was built around their stellar components: grand spirals of burning suns, ellipticals crowded with ancient stars, irregulars alive with star-forming clouds. Yet, as astronomical techniques improved and our surveys deepened, anomalies began to surface. Astronomers observed gravitational lensing where there should have been no visible mass. Hydrogen gas clouds swirled and rotated as though held together by unseen hands. These spectral structures hinted at massive collections of matter behaving like galaxies, but radiating little or no visible light. Thus emerged the theory of dark galaxies. Galaxies that possess the gravitational architecture of ordinary systems, but remain cloaked in obscurity. The primary signature of these entities lies in their hydrogen content. Neutral hydrogen emits radio waves at a specific wavelength, a spectral fingerprint that allows radio telescopes to detect and map vast clouds of interstellar gas. In regions where no stars are visible, but where this 21-centimeter line is strong and coherent, astronomers infer the presence of gas-rich galaxies that have failed to ignite into light. They rotate like galaxies, move like galaxies, and interact with other cosmic structures as galaxies do. Yet they shine with almost no visible light. These are the dark galaxies, whispering their existence through the quiet hum of hydrogen. One of the most compelling candidates for a dark galaxy is Virgo He 21, a hydrogen-rich cloud located in the Virgo cluster. This object exhibits a strong rotational signature, implying a massive gravitational source. Yet deep optical surveys reveal no stars. Its motion and mass distribution suggest it is bound by an extensive dark matter halo, providing the gravitational cohesion necessary to keep it intact. It is not simply a fragment or remnant. It behaves like a galaxy, just one in which star formation has been suppressed or never initiated. This brings us to the deeper mystery. Why would a galaxy fail to form stars? The process of star formation depends on the cooling and collapse of gas within a gravitational well. But if the gas remains too warm, too diffuse, or too turbulent, it cannot contract into dense stellar cores. Feedback mechanisms from nearby galaxies, cosmic reionization in the early universe, or even internal gravitational instability could prevent star formation from taking hold. In this scenario, the dark galaxy becomes a kind of frozen potential, a massive reservoir of raw material that never crosses the threshold into illumination. Dark galaxies may be more than rare oddities. They could play a foundational role in galaxy formation itself. According to simulations of the early universe, galaxies formed through hierarchical assembly. Smaller structures merge to form larger ones, building complexity over time. Many of the earliest building blocks may have been dark or nearly dark, aggregating gas and dark matter before conditions became right for star formation. In this sense, modern dark galaxies may be evolutionary holdouts, primordial remnants from an earlier cosmic era caught in suspended development. Moreover, these elusive structures challenge our methods of cosmic census. The luminous universe, the stars, the galaxies, the glowing nebulae, is only a partial map. If dark galaxies are numerous, then we may be drastically underestimating the number and distribution of galactic systems. Their presence may explain discrepancies in mass calculations for galaxy clusters, or the mismatch between observed and predicted satellite galaxies in galactic halos. The so-called missing satellites problem, the lack of visible small galaxies around the Milky Way compared to what models predict, could be partly resolved by accounting for non-luminous satellites that lurk just beyond the reach of our optical instruments. Detecting dark galaxies requires more than visual scrutiny. It demands multi-wavelength observations, gravitational studies, and careful modeling of gas dynamics. Instruments like the Arecibo Observatory before its collapse, and current arrays such as ALMA and the upcoming Square Kilometre Array are critical to mapping these spectral shadows. As technology advances, we edge closer to illuminating what has long remained in the dark. There is a poetic irony to these entities. In a universe defined by light, it is the dark that often holds the most mass, the most influence. Dark matter itself, which constitutes the majority of galactic mass, is invisible. And now, with dark galaxies, we face the reality that entire systems of stars may be ghostly in nature, not in the process of fading, but never having truly ignited. These silent structures, unlit but gravitationally active, are reminders that the cosmos is not limited to what we see. They demand humility in our exploration, a recognition that our senses and tools, powerful as they are, reveal only a narrow slice of reality. The fabric of the universe is woven with both presence and absence, and the dance between the seen and the unseen may be the key to understanding it all. And as we leave these hidden galactic phantoms behind, we are led to yet another cosmic mystery, one where light, rather than being absent, is bent, magnified, and sometimes multiplied. In Outline 16, we step into the extraordinary phenomenon of gravitational lensing, where massive objects warp the very shape of space itself, turning galaxies into cosmic lenses and revealing the deepest secrets of the universe through the curvature of light, galaxy clusters, and the cosmic web, the architecture of the universe. Emerging from the veiled domain of dark galaxies, those elusive, lightless scaffolds of cosmic evolution, we are now drawn outward into the grand design that holds the entire universe together, where dark galaxies represent the hidden microstructures of the cosmos, galaxy clusters and the cosmic web define its overarching form. This is the vast and dynamic framework upon which all matter, light, and movement are suspended. It is a structure that does not merely house galaxies, it organizes them, sculpts their motion, and dictates the paths of energy and time itself. Galaxy clusters are the largest gravitationally bound systems in the universe. They are not mere groupings of a few galaxies drifting near one another, but enormous congregations, often comprising hundreds or even thousands of galaxies, locked in orbit around a common center of mass. Bound by gravity, these clusters are enveloped in colossal halos of dark matter, threaded with streams of hot ionized gas and permeated by magnetic fields and relic radiation. They are not tranquil places. Within them, galaxies crash, merge, and strip one another of gas. These clusters are battlegrounds of evolution, where the past and future of galaxies are written in gravitational dynamics. Each galaxy within a cluster is like a single spark in a roaring bonfire. Some glide quietly through the intracluster medium, while others interact violently, distorted by tides and ram pressure, triggering bursts of star formation or extinguishing it entirely. The environment of a cluster can radically reshape a galaxy's fate. It can strip away the cold gas needed for star formation, turning spirals into ellipticals and quenching galactic youth in favor of ancient starlight. The physics at play within clusters is governed not just by gravity, but by the interplay of radiation, shockwaves, plasma turbulence, and dark matter flows. These vast regions are the laboratories of cosmic behavior. Yet even these massive clusters are not isolated. They are connected to one another through a deeper, more intricate structure, the cosmic web. This is the true shape of the universe, invisible to the naked eye, yet revealed through careful observation of galaxy distribution, gravitational lensing, and the behavior of intergalactic gas. The cosmic web is a filamentary network, a vast mesh composed of matter and energy stretching across billions of light years. Along its strands lie galaxies and clusters, while the spaces between, the voids, are eerily empty, almost devoid of galaxies altogether. This web-like structure emerged from the early fluctuations in the density of matter just after the Big Bang. As the universe expanded and cooled, gravity began to amplify these initial imperfections. Dense regions drew in more matter, growing into the filaments we see today. Simulations of cosmic evolution show this process with breathtaking clarity. We looked from a nearly uniform cloud of hydrogen and helium, the universe self-organized into a textured lattice, a universal framework of filaments and nodes where matter congregates and galaxies ignite. The intersections of these filaments are where galaxy clusters reside, often forming superclusters, mighty agglomerations of matter stretching hundreds of millions of light years across. One of the most massive such structures known is the Lagrangian supercluster, the home region of our own Milky Way. This immense gravitational basin spans over 500 million light years and contains more than 100,000 galaxies. all flowing toward a common gravitational center. Laniakea is not a separate entity from the cosmic web. It is a node within it, a swelling along a cosmic artery, part of a vast cosmic river flowing through intergalactic space. The cosmic web also provides crucial insight into the nature of dark matter and dark energy. Since most of the universe's matter is invisible, we detect it not by light, but by its influence. The shape and density of the web, the motion of galaxies along its threads, and the warping of light by its gravitational wells all serve as indirect measures of the dark scaffolding that underpins reality. Even the temperature and density of the intergalactic medium within the web's filaments tell stories of heating by quasars, shocks from gravitational collapse, and the chemical enrichment of the universe over time. In recent years, the cosmic web has come into sharper focus, thanks to sky mapping surveys like the Sloan Digital Sky Survey and space-based observations from missions such as Planck. These projects have charted the positions and motions of millions of galaxies, revealing not a random distribution but a finely structured tapestry. The universe is not chaotic. It is exquisitely ordered at scales that dwarf comprehension. Beyond its scientific significance, the cosmic web evokes a profound philosophical perspective. Its resemblance to neural networks has led some thinkers to draw analogies between the structure of the cosmos and the structure of the mind. While this comparison is speculative and metaphorical, it forces us to ask, is the universe a machine, a living system, or something beyond all categories we understand? The web, with its connections, flows, and branching logic, appears not as a random scattering of matter, but as a deliberate unfolding, an expression of laws deeper than we yet know. And so, from the dark, starless realms of invisible galaxies to the glowing strands of the cosmic web, we come to see the universe as a layered creation, each level of structure building upon the last. It is not a place of mere explosions and voids, but of patterns and architectures, woven with energy and time, forged by the gravity of what is seen and the mystery of what is not. Now, as we trace the light and mass along these cosmic filaments, we are drawn toward yet another phenomenon that bends not just light, but space itself. In Outline 17, we journey into the realm of gravitational lensing, where matter becomes lens and space becomes canvas, revealing hidden galaxies, dark matter halos, and the warp geometry of the universe, the Helix Nebula, the eye of space. From the cosmic web's grand lattice work, threading galaxies, matter, and gravitational influence across billions of light years, we now focus our gaze on something far more intimate and haunting. We leave behind the enormous scales of interconnected filaments and plunge inward into the fate of a single star nearing the end of its life. What we find is a structure so delicately beautiful, so eerily symmetrical, that it has been called the Eye of Space. It is the Helix Nebula, a dying star's final exhalation frozen in luminous color, floating in the dark like a celestial iris, staring back at creation itself. Located in the constellation Aquarius, the Helix Nebula is among the closest planetary nebulae to Earth, offering an exquisite view of the stellar death process. But despite its name, a planetary nebula has nothing to do with planets. The term is a relic from early astronomers who, peering through primitive telescopes, saw round, disc-like shapes resembling distant planets. In truth, a planetary nebula represents one of the final stages in the evolution of a medium-sized star, like our own Sun, and the helix is one of the most well-studied and vivid examples of this cosmic transformation. The story of the Helix Nebula begins with a star that spent billions of years quietly fusing hydrogen into helium, radiating warmth and anchoring a solar system. Over time, as the hydrogen in its core was exhausted, the star grew unstable. Its outer layers expanded, becoming a red giant, and eventually gravity could no longer hold the envelope of gases against the pressure of radiation and stellar winds. The star shed these layers into space, forming expanding shells of gas and dust. What remained at its core was a white dwarf, an Earth-sized, incredibly dense stellar ember emitting intense ultraviolet radiation. That radiation illuminates the surrounding gas, making the Helix Nebula visible. The result is a glowing, multicolored structure shaped by fluid dynamics, magnetic fields, and centuries of stellar winds. The central region glows blue from ionized oxygen, while the outer edges burn red and orange from hydrogen and nitrogen. At the center of this stunning display, the white dwarf glimmers faintly, like the pupil of a ghostly eye. One of the most intriguing aspects of the Helix Nebula is its complex internal structure. What appears to be a simple ring is, in fact, a multi-layered cylinder, an illusion created by viewing a three-dimensional object from a single angle. Advanced imaging has revealed filamentary strands, comet-like knots, and radial spikes of material, all moving outward into interstellar space. These cometary knots, each larger than our solar system, are dense clumps of gas with long trailing tails pointing away from the central white dwarf, shaped by photoionization and pressure gradients. Their existence was once unexpected and now remains a subject of deep astrophysical interest, as they may influence the final dispersal of the nebula. The helix is not just a pretty sight. It is a stellar autopsy, a snapshot of what will eventually happen to the Sun. Billions of years from now, our star will swell, shed its layers, and become a white dwarf surrounded by a planetary nebula. The Earth will likely be consumed or left as a dead, frozen relic drifting through space. The helix, then, offers not only beauty but foresight. It is a window into both our origin and our destiny. The carbon, oxygen, and heavier elements, scattered by the death of stars, like the one that formed the helix, are the very materials from which planets, oceans, and organic life arise. In its death, the star becomes a seedbed for new creation. Observations of the helix across different wavelengths, from visible light to infrared and X-ray, have revealed more than just glowing gas. They show shock fronts, interactions with the surrounding interstellar medium, and the cooling paths of matter as it disperses into the galaxy. This nebula is not an isolated event, but part of a continuous cycle in which stars are born, live, die, and return their elements to the universe, enriching future generations of stars and planets. There is something deeply human in the Helix Nebula's gaze. Across cultures and civilizations, eyes have symbolized awareness, vigilance, and the soul. To look upon the helix is to feel observed by the cosmos itself, as if the universe, through its processes of creation and dissolution, bears witness to its own unfolding. Its symmetry speaks to order within decay, structure within entropy, and its silent light, traveling across hundreds of years to reach us, reminds us that we are part of this grand stellar continuum, that the atoms in our blood once burned in stars and will one day return to them. The helix is more than a structure. It is a metaphor made real by Astrophysics. In it, we see the convergence of beauty and finality, science and symbolism. It teaches that the end is not an end at all, but a transformation, a dispersal of being into wider fields of possibility. And as we drift from the eye of space, we are once again invited to look further, not just with our instruments, but with our imaginations. From the disintegration of a single star, we now move to the bending of space itself. In Outline 18, we explore the astonishing realm of gravitational lensing, where gravity becomes not just a force, but a lens that reshapes light and behind the veil of distance and time.